Yeah, good morning, everybody. So before we start the program, just a reminder about the tour in the afternoon starts at 4:30. Yeah, not 3:30. There was a typo. 4:30 in front of the meeting point is in front of this building. And it will lead you, for those who attend dinner, it will lead them to the dinner place. Okay, and if you bought the dinner but you don't feel well, yeah, please don't come. Yeah, we don't need any COVID outbreak in this conference, and yeah, please also test yourself if you are unsure. Okay, thank you, and I will hand it to Einan, who will chair the first session.
Thank you very much. It's a real pleasure to start Wednesday morning session. So welcome everyone. And our first talk today is by Lance Dixon. It would be about antipodal duality and the 8-loop application. Please.
Thanks a lot, Einan. It's a real pleasure to be able to give a talk at this very inspiring conference at the beautiful heart of Prague. It's great to see everybody again after a long period of isolation. And I wanted to tell you today about some work that I've been doing principally with Omer Gordogan, Andrew McLeod, and Matthias Wilhelm. A paper came out in December, and then some more related work in April. And that will be the bulk of the talk. And then the 8-loop application was done with a student, Andy Liu, which we're still finalizing. But the gist of the story can be told on one transparency. We calculated 6 gluon scattering amplitudes in planar n equals 4 super Yang-Mills theory to 7 loops in the MHV configuration. And then a little later, we calculated a certain form factor which resembles a Higgs boson interaction with gluons. The operator involves the field strength for gluons squared. We calculated the 3 gluon form factor to 8 loops, and that has only kind of an MHV independent configuration. And then we looked at the two, and we discovered they were written backwards from each other. It's like someone told you to read the Encyclopedia Britannica, and 40 million words later, after you finished, they told you it makes sense backwards, too. So that's how surprised we were. And so I'll tell you a little more about the details as we go along. Both sides of this duality are functions that are multiple polylogarithms, and we heard some about them in their structure already at this conference, for example, from Song He and Simone Zoya. And they're iterated integrals. Very simple examples of iterated integrals are the classical polylogs, Lin of x. They can be defined recursively by integrating dt over t from the classical polylog with one lower index. And the very first one, Li1, is minus log of 1 minus t over t. And so there's a grading or a weight associated with these functions, or more general iterated integrals. And the general rule that has been found is that in planar, even non-planar n equals 4, the amplitudes have uniform weight. That is, the number of integrations needed at loop order L is of order 2L. And this is much simpler than in, let's say, QCD, where you often get all weights running from 0 to 2L. There's another very important duality that has already been the focus and underlies much of the research in planar n equals 4 scattering amplitudes, which is that scattering amplitudes in this theory are dual to the expectation values of Wilson loops. So if you have a certain number of massless gluons coming out of the process, and you calculate Feinman diagrams for this process or some other way of producing the loop amplitude, it's equal, at least when you define a suitable finite quantity, it's equal to the expectation value of a polygonal Wilson loop that can emit gluons off of it that interact in kind of form a planar web. And this picture also underlies a symmetry of the pure gluon scattering amplitudes in this theory, or all massless scattering amplitudes, which is that the amplitudes can be thought of as depending on the corners of the polygons, which are not really positions, although they're denoted by x, but dual momenta. But they transform like positions under a conformal symmetry of the x's. And this duality holds at both strong coupling and weak coupling. That is to say, it's true order by order in the coupling. So the dual conformal symmetry inverts these corners of the polygons, or that's the key generator that you need to study invariance under. When you perform this inversion, the invariant intervals transform up to these products xi squared, xj squared. So just like position space conformal invariance in conformal field theory, the invariant function should be built out of invariant cross ratios. But in this case, we have a constraint, which is that the xii plus 1s are null, so you can't use them to build the cross ratios. So whereas in sort of ordinary conformal field theory, you start with the 4-point function, that's the most interesting key. In our case, it's the 6-point function. Because of these null distances, you can't build any cross ratios when you have only 4 or 5 external legs or 4 or 5 corners. Once you have 6 corners, you can build this cross ratio here, which is kind of indicated by this box where we've just switched 3 and 4 from numerator to denominator. If we recall the definitions of the xij squareds in terms of the momenta, they're built out of Mandelstam variables. And the numerators of these cross ratios are 2-particle Mandelstams, and the denominators are 3-particle Mandelstams. And that's one of 3 that you get because you can use dihedral symmetry to work out the other 2. So we're going to call these U hat, V hat, and W hat. And they're the underlying dimensionless conformally and dual conformally invariant variables for the 6-gluon scattering problem in planar n equals 4 super Yang-Mills theory. So this system's been studied for a while. We've been working on bootstrapping it up from, say, 3 loops to 7 loops in a series of papers that mostly finished in 2019 with one still hanging around. But all of the results to all the loop orders, we think, to all loop orders, but definitely to 7 loops, the results are generalized polylogarithms. And in contrast to what often happens in complicated QCD processes, you get to use the same symbol alphabet to all loop orders. Well, actually, at 1 loop, you don't see quite all the letters yet. But once you get to 2 loops, you've seen all the letters, and it's a very simple alphabet, as we'll see. And the same basic process of bootstrapping on a polylogarithmic function space was also used in this more recent form factor construction. So, and in order to implement this bootstrap, we need some boundary data, and we get it from an OPE approach to calculating amplitudes and more recently form factors in the near collinear limit. So the former for amplitudes was pioneered by Basso, Sever, and Vieira, and the more recent one is due to Sever, Tumanoff, and Wilhelm. So there's this 3-dimensional phase space, and it's very intricate, and there are many different limits you can discover, and I won't really say too much about them here, but this green line, that's where we get the boundary data from. This is the limit that is described by an operator product expansion with a small number of excitations. So just a quick primer on generalized polylogarithms and the symbol. You can define these as iterated integrals, where you're always integrating a d log, like this one, dt minus a1, over something iteratively that was already such an iterated integral. And the number of integrations is, again, the weight, n. But these, in different contexts, these a's can depend on the underlying variables, and also x, in a particular way. And it's more convenient to define a whole system of functions differentially. They're all these iterated polylogs, but when you define it this way, you can ask this differential to decompose into a finite sum of d-logs, where these sk's are functions of the underlying variables, and they belong to some symbol alphabet, curly L. Now, there's a more general Hopf algebra that coacts on the space of polylogs, and it takes functions to pairs of functions of lower weight, where the sum of the weights here adds up to here. The derivative is one piece of this operation. It's the case where the weight splits as n minus 1 and 1, because the d-log is a weight 1 object. So in general, we would write the coaction as with a tensor product, and this piece, the n minus 1 comma 1 piece, is essentially just the first derivative. It's just repackaged slightly. And then you can go on from that and take derivatives of these guys and continue. So again, these SKs are called letters, and they belong to a set, the symbol alphabet. So if we keep applying this n minus 1 coaction iteratively by taking derivatives of the weight n minus 1 guys, the FSJs, that defines some Fs with 2 indices on them, each one in the symbol, carrying an index in the symbol alphabet. And so we can keep doing this and iterate n times for a weight n function before we stop. And the symbol is a rank n tensor, and all of its coefficients at this stage are just rational numbers. So it's very much of a, these letters make up words, and at loop order L, they have length 2L. So when we get to 8 loops for the form factor, we have words of length 16, for example. One simple example of this is where the letters belong to a 2-letter set, which is kind of binary. So in that case, everything can be encoded in a binary string. And the corresponding functions, we could have used the G notation, but the physicists also use a slightly different notation called harmonic polylogarithms, and these date back to work of Remedia and Vermasren. And so you just record with either a 0 or a 1 what the last integration was. Was it dt over t? You put a 0 in front. Or was it dt over 1 minus t? You put a 1 in front. And correspondingly, the derivatives only involve d log x and d log of 1 minus x when you differentiate these formulas. So from this, these formulas here, we can see that the symbol alphabet only involves 2 letters, x and 1 minus x. And you can compute the symbol of an h of any w in terms of things that are either x or 1 minus x. Now, the branch cuts are dictated by the first integration. So you start off with a logarithm, which is either log of x or log of 1 minus x, and that has a discontinuity, different locations. And then as you do successive integrations, that discontinuity gets modified and integrated, but its location stays in the same place, either x equals 0 or x equals 1 in this case. So that's a general statement that the branch cuts are dictated by the first entry in the symbol, whereas the derivatives are dictated by the last entry because of the recursive definition we had for how we build up the symbol and look at the d log when we differentiate. So there's a quite different role that's played by the first and last entries. So now it was realized very early on that the symbol alphabet for the 6-gluon MHV amplitude, at least at 2 loops, and it turned out to be true to much higher order as well, has only 9 letters in it. 3 of them are just the cross ratios that I've told you about before, which are ratios of Mandelstam variables. And then also 1 minus the cross ratios can be used to give 3 more letters. And then there are 3 more complicated letters, which have a simple representation in terms of momentum twisters. But in the end, we're not going to actually need them for the bulk of this talk. There are some algebraic functions of u hat, v hat, and w hat. But they're odd under a certain parity transformation. And you can find a region where they're all irrelevant by going onto a surface of the kinematics which preserves parity. And one way to do this is to smash the 5 independent vectors in the 6-point process down into a smaller space. And one possibility is to choose to do it in a kind of cyclically nice way where you choose the I plus third halfway around the hexagon to be the negative of the one. So like K4 hat would be minus K1 hat, and K5 hat would be minus K2 hat. When you impose this constraint, in terms of these dual conformal variables, it picks out a surface, which is a kind of Graham determinant polynomial, that is cubic in these variables. And here I've shown the variables u hat, v hat, and w hat from the same orientation as before. There's a unit cube, which I didn't quite show. And inside the unit cube, there's a tetrahedron. And if you sort of puff a little air into the tetrahedron, that's what this surface looks like. So on this surface, the symbol alphabet does not have 9 letters. It only has 6 letters. That'll be important later. I should also say that all these amplitudes, strictly speaking, are divergent in 4 dimensions. But we know up to constants how to remove all of the infrared divergences. The leading divergences are associated with soft and collinear exchange of gluons between hard external legs of a scattering amplitude. And they're dual in the Wilson loop picture to ultraviolet divergences that come from renormalizing a cusp. So that's called the cusp anomalous dimension. And this connection was first pointed out by Korchemsky and Radushkin. And this cusp anomalous dimension is known to all orders in planar n equals 4 due to the work of Beissert, Eden, and Staudacher. Now, there's a formula that involves the cusp anomalous dimension and the exponential of the one-loop amplitude called the BDS ansatz. And then there's a little more minimal version of it that has some nice properties that in both, that it only depends on the 2-particle invariance. So there's something that contains all the IR divergences and only 2-particle invariance, and we divide the amplitude by it. When we do that, the remainder only depends on u hat, v hat, and w hat. It's closely related to an earlier quantity called the remainder function, but it has better structural properties, this quantity A6, because we've only divided by something involving 2-particle invariance. And the reason it has better structural properties is at least partly related to a principle called the Steinman relations. So the Steinman relations were pointed out in 1960, and they state that there are causal restrictions that forbid you from having overlapping branch cuts, consecutive branch cuts in overlapping channels. And an example of an overlapping channel would be 3, 4, 5 and 2, 3, 4. Those both contain the set 3, 4. So they divide the process into 2 pieces, and the external states are not the same and are not subsets in the 2 cases. And one way to understand the Steinman relations for 3-particle invariance in the 6-point case is to go to 3 goes to 3 scattering. And within 3 goes to 3 scattering, you have regions where it almost resolves into 2 goes to 2 and then a second 2 goes to 2. And that's what this indicates. And that in a multi-loop process, you could have many particles sort of traveling along there. And as you change the external kinematics very gently, the only thing that happens is the 3-particle invariant switches sign, and you open up a discontinuity. And so Steinman basically argued that if you have a situation where you have both access to both channels in the same region, that there's a analytic region that should lead to this statement that these double discontinuities vanish. And he was considering manifestly infrared finite theories with mass gaps and so on. But the same argument apparently works here as well in the fully massless case. But if you want to make something finite and you have that finite thing depend on the 3-particle invariance, it messes up the Steinman relations. And that's why it's important that there are 2-particle invariant quantities that you can remove all the divergences from. So now this Steinman relations, which are phrased here in terms of non-dual conformal invariant quantities, we can manifest them if we change the alphabet. So I mentioned that the alphabet involved these 6 letters, but we can make a multiplicative change of the letters. In particular, for the Steinman part, we change from U hat, V hat, and W hat to A hat, B hat, and C hat. And the reason for doing that is if you follow back to the definitions, you'll see that these guys only depend on one 3-particle invariant at a time. And because of that, this statement translates directly into a double discontinuity statement for the finite quantity that only depends on U hat, V hat, and W hat. And we found an extended version of this, which this would normally just say that A hat can't be next to B hat as the first slot in the symbol. But we found that it also holds at arbitrary locations in the symbol. So we have a set of restrictions like this, which help us trim down the hexagon function space. So now I want to switch quickly to the other character in the story, which are these 3 gluon form factors, which are like Higgs matrix elements through a very heavy top quark. They involve this operator, the field strength, or other representatives of it in the chiral stress tensor multiplet of planar n equals 4. And we again choose this guy because it's the simplest one that isn't too simple. In other words, if we only had 2 gluons, we would have no kinematic dependence at all. And this only depends on 2 dimensionless ratios. And so we can plot sort of the kinematics in this plane. There's some decay region where a Higgs or operator decays to 3 gluons, some scattering regions. And using the basic kinematic relations for 2 goes to 2 scattering, we have these 3 dimensionless ratios, U, V, and W. No hats on these guys. And we introduce W, even though it's not independent of U and V, because there's a D3 dihedral symmetry that is more manifest when you include W. U, V, and W cycle into each other, or you can swap any pair, and that generates the dihedral invariance. The dihedral invariance in the hexagon case is D6, but on the parity subspace, it drops to D3, matching the dihedral symmetry here. And a typical one-loop integral for this process is easy, well known to include these dialogues. If you calculate the symbol, you see U, V, 1 minus U, 1 minus V. And if you cycle these legs around to include some other diagrams, you find this symbol alphabet here. And the same symbol alphabet was also seen at 2 loops in work in QCD by Thomas German et al., and in n equals 4 about a decade ago by Brandhuber, Travellini, and Yang. I'm going to skip through this next part for lack of time. But motivated by the previous transformation in the 6-gluon case, we also looked at the same transformation without the hats in this case. And we found that it dropped the size of the symbols remarkably. Also, we consider the BDS-like normalized form factor in parallel to what we did for the amplitude. There's also a BDS-like ansatz here. So the symbol becomes very simple. At 1 loop, it just has 1 term, B tensor D, plus dihedral images to make 6 terms in all. And even at 2 loops, it has only 12 terms. These 2 plus the images under these dihedral transformations. So finally, I can state what the duality we found is. And it says that the form factor is the antipodal map on the 6-gluon amplitude, evaluated here at U hat, V hat, and W hat, and here at U, V, W. And they're related by this relation, this kinematic map. You can check easily that if you impose U plus V plus W equals 1, this maps you onto this surface delta equals 0, which, as I said before, corresponds to this kind of kinematic constraint, which we think of as some kind of twisted forward scattering. And when you do this map at the level of the letters of the symbol alphabet, it's not hard to show that it exchanges the square root of A hat on the amplitude side for D on the form factor side. And D hat on the amplitude side goes to A on the form factor side. And then you just cycle these to get the rest of the relations. And these are the formulas for the 6-gluon amplitude at 1 and 2 loops that you can get from this substitution and it looks almost identical except some factors of halves were put in there. And that also, I forgot to say, the symbol antipode map on the symbol reverses the order just like this. There's some -1 to the m, but we're always talking about even weight symbols, so it's always +1. So we checked this for all the terms in the symbol, and we had computed at 7 loops on each side. And so at 7 loops, that involves comparing 92,954,568 terms, which is about twice the number of words in the Encyclopedia Britannica. And since then, we've been working at 8 loops, and basically it works too, although we use the input to help us solve equations, and that's 1.67 billion terms. So the map covers the whole phase space. I'm going to skip through the evidence we have beyond the symbol, but this antipode map covers lots of stuff beyond the symbol. In particular, the duality predicts that these blue numbers here, which are some representations of multiple zeta values, they have to be the same on both sides, and they are. And I just mentioned that this explains some adjacency restrictions we had seen on the form factor side. We don't understand the duality, but it takes things that we understand more or less from causality and maps them into things that were totally bizarre. So in the last minute, I'll just mention that with Andy Liu, we exploited the duality. We had 8 loop results in the form factor. We mapped them over by flipping the symbol around and applying this map, and they gave us the results for the symbol on this surface. And then we need to lift off the surface into the bulk. And in principle, there could be ambiguities, functions that vanish on the surface but not in the bulk. It turns out there are no such ambiguities until 6 loops. And then there's one ambiguous function. At 7 loops, there are 3 functions, but they're in a dihedral orbit. When you impose that, you get 1. And in this case, you get 3, but you can completely determine them very quickly. So it's a very efficient way to get 6 gluon amplitudes if you're given the form factor. And we have predictions here that are satisfied by the result, which is the value expressed in terms of multiple zeta values in a nice form for seeing the duality. And everything's nice and consistent. Andy has since found an antipodal symmetry, which works to 2 loops, but not yet beyond. It's a little bit different. But I'd like to summarize here just by saying that we found this strange duality. We still don't understand it at all. Or to phrase it as Nima might, what is the question to which antipodal duality is the answer? Could it be related to flux tube representations? There's some hints. How does it hold its strong coupling? I think some people are looking at that. We would really like to understand if it holds at the next most simple case, which we think should relate the 8 gluon amplitude to the 4 gluon form factor. But we don't have anything working there yet. And that might help us tell more what the meaning of it is, and also this symmetry that Andy found recently. And how much more can we exploit this in order to learn more about what are the true structures underlying both amplitudes and form factors. Thanks a lot.
Thank you, Lance, for a beautiful talk. So it's open for questions. Yes?
My question's on your slides. So I wanted to know if you had any intuition or any toy models of simple examples where you understand what antipodal symmetry means. I mean, seems like a very severe change in interpretation.
When you say antipodal symmetry, so
I mean,
that's what Andy called it in his map, or do you mean the...
I just mean if I take a iterated integral and I exchange discontinuities for derivatives, what...
I mean, there's some hint from lower loop, one loop integrals in different dimensions. So Nima Arkanihama and Ellis Yuan, they found some dual relations of integrals that exchange things, but they don't really look like exactly the right operation because those mapped massless integrals into integrals with internal masses. We've also asked ourselves if we apply this operation not on the full amplitude, but on some natural integrals. There are these, in the hexagon case, there are these sets of of ladder integrals, they don't actually satisfy, they don't live in the dual space. Sometimes they actually have the right final entry to have the right first entry on the map side, but then they might not have the right second entry. Or if they have the right second entry, then at the next loop, or the higher you go in loop order, the more of these entries they satisfy, but not all of them. So what we do know is it's important to add everything up into the right quantity somehow.
Yes. Now,
Actually, I have microphone. So
you get it.
Is the space of integrable symbols invariant under the antipodal reversal?
Well, we have not, so we work with a space that also has these Steinman conditions on it too.
Okay.
And that space is invariant, but it's almost by definition. Because our definition of the space in the end is the minimal space that contains all the amplitudes and all of their derivatives. In other words, as we go along, we chuck out functions every time we discover that they can't be derivatives of some amplitude. So then once you say that, then since the whole space is built by taking kind of the coproducts of amplitudes, then if the amplitudes map, then the whole space maps, because it's sort of tautology. But we haven't explored the case of whether we could, I mean, let me say it, but let me try to answer your question a little better. We need these final entry conditions on the amplitude itself. If you don't impose those, then it won't map to the other space because we always define the other space with first entry conditions, a restricted set of symbol letters on each side. In this case, it's exactly half. 3 of the letters can be in the front, 3 in the back. So without that condition, the spaces won't map.
Thanks.
Yeah. Okay. Yeah.
yeah, in your final formula at 0.111, the numerology question. You had,
so the 8-loop one, like this?
yes, on the final line you have these rational numbers, but you have zeta 2 and zeta 16. Did you try to rewrite it in terms of other zetas with integers?
No, but sometimes when we get lousy numbers in the bottom, we ask, are they because of the relation between pi to the 2n and zeta of 2n? Like maybe at zeta of 12 there's a 691 in there, and so when you write it in terms of zeta 12, you often get, not in this case, but in a lower loop case, you get a 691 in the denominator. And I think, part of that factor in the denominator would be removed if you wrote zeta to 16. But we have not tried to, in this case, write it as integer linear combinations. But we do notice that everything's integers except where you have this zeta 2n ambiguities from combining different terms. So this is really an integer problem. And there are a huge number of integer sequences that run through these spaces of symbols. Humans, like us, can find some of the patterns to all orders, but there are probably a lot more patterns that only machines can discover, unless we get smarter.
Yeah. Yes, please.
I missed something about you reducing the symbol alphabet from 9 letters to 6 letters. You were choosing a particular phase space point where the scram determinant vanishes. And so
it's not one point, it's a two-dimensional, it's a codimension 1 surface or a two-dimensional surface where all those 3 letters vanish, or they go to 1.
Can you, from that, determine the full amplitude as a function of all the 9 letters, or does
Yeah.
it not actually depend on the other 3 letters?
No, it depends on the other letters. So this is what we did at 8 loops. But let me just tell you that at 5 loops, it's like trivial. Once you've fixed the function on the surface, our function space contains no parity, and the function has to be parity even. There are no parity even functions at 5 loops or any lower loop that vanish on the surface and are non-vanishing off the surface. So that means it's uniquely fixed by the value on the surface. Now at 6 loops, there's one parameter, so you have to fix one function, and there are multiple ways you can do it from going to different points.
So at 8 loops, you have the full answer, or just?
Yeah, we have the full answer. In fact, this is like our cryptogram that says we have the full answer. because we have the full numerical result at this point, not just for the symbol, for the full function. We can specify the function anywhere you want. We'll make some plots soon. But yeah.
Okay. Yeah, I think we'll have to stop the discussion at this point. Clearly, there are many, many more questions to answer on this. So thank you very much, Lance. So we are ready to start the next talk on this session. So, okay, are the slides available? Yeah. Okay. So the second talk today is by Matthias Willem about symbology of elliptic Feinman integrals and scattering amplitudes. Please go ahead.
Thank you. Let me start by thanking the organizers for putting together this very nice conference and for inviting me to speak here. My talk will be based on work from last year together with my former student Alexander Christensen and my postdoc Zhezhang. Then another work from 2 months ago with Zhezhang and ongoing work also with my postdoc Anne Spiering, my PhD student Roger Morales, and Xingying Yang from Beijing. Zhezhang is applying for postdoc positions this fall, and he's very strong, so keep an eye open for his application. The bigger question behind my research work here is to understand what numbers and functions occur in quantum field theory. Moreover, we'd like to understand how we can use this knowledge to exploit our calculational reach. These numbers and functions are relevant, for example, for Higgs physics at the LHC, but also for the G-2 of the electron or the post-Minkowskian expansion of gravitational waves. At one loop order, the functions we encounter in quantum field theory are polylogarithms. For example, the one-loop bubble integral here in 2 dimensions with massive internal propagators evaluates to a logarithm, and the one-loop box in 4 dimensions evaluates to dilogs plus a product of logs. At higher loop orders, if we are looking at sufficiently simple quantities, the Feinman integrals we encounter evaluate to Gonchov polylogarithms, which are simple iterated integrals with d-log integration kernels. These come equipped with a very powerful tool called the symbol, which can be defined recursively via the total differential. The differential of a Gonchov of weight n here is given by a sum of Gonchov polylogs of weight n-1 times a d-log of phi I, where phi I is a rational or algebraic function of the momenta or masses. The symbol is then recursively defined as the tensor product of this logarithm of phi I times the symbol of this lower weight function. And in contrast to Lance, I'm picking also the log here to be part of what I call the symbol letter. Now, due to the symbol, the identities of polylogs are very well understood, which has many applications, and we've heard from some of them already during this conference, and I believe that we'll hear about some more further on today and later. So, in a nutshell, the idea behind the symbol is to decompose complicated functions to simple functions. The application that originally introduced the symbol to the physics literature is, of course, the dramatic simplification of the 2-loop 6-gluon remainder function from 18 pages to 2 lines. Moreover, also the symbol alphabet was investigated, and for 6 and 7 gluons, it was found to be related to cluster algebras in n=4. And on Monday, Song told us about how this can be extended also for more general sketching amplitudes and Feinman integrals. Now, once you have your symbol alphabet, you can write down a basis of functions for the space in which your answer has to live. And then you can make an ansatz with coefficients, and if you're lucky, you have sufficiently many physical constraints to be able to fix all of the coefficients and uniquely single out your answer. This goes under the name of symbol bootstrap. And it has been in particular used to bootstrap the 6 gluon remainder function up to 7 loops, and Lance has just told us about 8 loops, and the 7 gluon one up to 4 loops. However, this doesn't stop at n equals 4 or these amplitudes. We can also use it to bootstrap individual Feinman integrals, master integrals, as solutions to differential equations. Moreover, as Lance has just told us, the latest thing we've been able to bootstrap is this 3-gluon form factor that is related to Higgs physics up to 8 loops. And in the part that he skipped, based on 2-loop evidence, we would expect that this also gives the maximum transcendental part of the Higgs to 3-gluon amplitude in planar Young-Mills, now without the super here, and also revealing a surprising duality. However, quantum field theory doesn't stop at multiple polylogarithms. We can also encounter more complicated functions in Feinman integrals. One family of these is the banana family, now in 2 dimensions with massive internal propagators. And at 2 loops, this evaluates to elliptic integrals, and at L loops to integrals over Calabi-Yau L-1 folds. And these have a lot of phenomenological applications. Other families we were able to identify are these train tracks, now in 4 dimensions, massless internal propagators, also evaluating to Calabi-Yau L-1 fold integrals, or these tardigrades, now non-planar, but getting twice the dimension at each loop order to L-2. And these are, in particular, the only contribution to a particular component amplitude in maximally supersymmetric planar n equals 4. So they also occur in arguably the simplest quantum field theory. The question is now whether we can develop a similar understanding and similar techniques for these functions as we have for multiple polylogarithms. In my talk, I'll address this question for the case of Calabi-Yau 1 folds, which are elliptic curves. I'll start with a review of elliptic generalizations of polylogs. Then I'll introduce you to elliptic symbology for these. And indeed, I find that this reveals some hidden simplicity and some structures that indeed allow us to bootstrap these functions. The prime examples here are the 2-loop sunrise integral with masses and in 2D, as well as this 10-point double box integral with massless internal propagators in 4D. So let's start with elliptic polylogs. One way we can see that we encounter elliptic functions at Feinman integrals is via Feinman parameterization. So let's say after doing some of these integrals, we encounter a square root of a polynomial of degree 3 or 4 in the remaining integration variable without coinciding roots. Now, we might just call this polynomial y, and now y squared equal to this defines us an elliptic curve, which I've shown here, depicted here in Weierstrass normal form. Now one can also define elliptic polylogs on this elliptic curve, similarly as Gontroff polylogs as iterated integrals, but now the integration kernels here are psi n. Psi 1 is just the usual d-log, the kernel we have for Gontroffs. So elliptic polylogs contain Gontroff polylogarithms. Moreover, we also have psi 0, which is 1 over y, and psi minus 1, which is kind of the product of the two normalized such that it has unit residue. In addition, there's also infinitely many more kernels. While this version of elliptic polylogs occurs directly in Feinman parameter integration, the functions here aren't pure, so we cannot define a symbol for them. A second version of elliptic polylogs uses the relation between the elliptic curve and the torus, which is defined as the complex numbers divided by the letters generated by the periods omega 1 and omega 2. To go from the elliptic curve to the torus, we can use Abel's map, and to go back, we can use the Weierstrass P function. It's important to note that each kinematic point C here corresponds to 2 points on the torus, essentially because of the sign ambiguity of the square root here. And thus, there's also 2 images, the plus and minus image on the torus, which we denote by ZC plus minus. Now, the second version of elliptic polylogs lives on the normalized torus, where we define tau to be omega 2 divided by omega 1, and W to be Z divided by omega 1. These gamma tilde functions are also defined via iterated integrals, but now the integration kernels are generated by the Eisenstein-Kronecker series. So here the theta 1 is the odd Jacobi theta function. One interesting property of these functions is that the length, which is the number of integrations, is not necessarily equal to the weight, which is the sum of these n I here. However, these functions are pure, so we can indeed define a symbol for them. To go back and forth from the E4 functions on the elliptic curves to the gamma tilde functions on the torus is relatively easy because the integration kernels of the former are given as linear combinations of the integration kernels of the latter. Now let's turn to the symbol. Recall that the symbol of a multiple polylogarithm can be recursively defined via the differential. Similarly, one can also define the symbol of such a gamma tilde function via the differential. And here now, this is a gamma tilde function of length reduced by 1. And the form here, d omega, is what replaces d log. So in particular, omega will replace the log as the symbol letter. And the omegas are the primitives of the G kernels with respect to W. Now, here I've actually defined the derivative and the symbol for gamma tilde underscore, which differs from gamma tilde by some factor of 2 pi I to the power of the length minus the weight. This is such that if we go to a kinematic limit where the elliptic curve degenerates, the elliptic letters degenerate to logs without additional factors of pi, and the same for elliptic polylogs. Now, in order to manipulate elliptic symbols, we need to know the identities that the elliptic letters satisfy. So the analog of log A plus log B equals log AB. A simple such identity is that for J being even, this omega J is odd in W, and for J odd, it's even in W. Moreover, these G functions and thus the omegas are, strictly speaking, only defined on the universal cover of the torus. So if we shift W by tau in omega n, this is only equal to omega n up to omegas of lower weight. We can obtain one further identity by recalling this relation between the d-log kernel, which can also be written as a sum of g1s. Now, integrating this on both sides of the equation from a to b, we can rewrite a logarithm as a sum of the primitives of the g1s, the W1s. However, this doesn't exhaust all identities between the omegas. As I'll tell you in detail further on, we can find further identities for omega 1 and 0 via Abel's addition theorem, and for omega 2 by defining a symbol prime. In order to apply Abel's addition theorem, we consider our elliptic curve here, defined by a quartic or here a cubic, and consider another curve with coefficients bi that intersects this curve in 3 points, which we denote as xi, yi. Now, Abel's addition theorem goes back to almost 200 years, and it tells us that while the integral of a rational function on this elliptic curve might be complicated, the integral up to the intersection points, summed over all intersection points, is simple. It can depend at most logarithmically on these coefficients in the second point, curve here, bi. So the first rational function we want to apply this here to is dx over y, which gives us the torus images of our kinematic points C. Now, Abel's theorem tells us that the image of x1 plus the image of x2 is equal to the image of x3, which gives us an identity for omega 0, since omega 0 is just proportional to w. A second kernel we can apply this to is psi 1, which is also a rational function on the curve, and can be written as a sum of g's. And via Abel's addition theorem, we obtain a second identity for a sum of omega 1s and logarithms. What now about identities for omega 2? There are indeed such identities known, the elliptic Bloch relations, which generalize this famous 5-term identity for the Bloch-Wigner dilogarithm to the elliptic Bloch-Wigner dilogarithm. However, already for the dilogarithm, we don't actually use the 5-term identities in modern applications to simplify it. Indeed, we use the symbol. The problem now is that this omega 2 is already a simple letter. We cannot use the symbol to decompose it further. Our idea was thus to define a symbol prime that does the same job for omega 2 that the symbol does for polylogs. To this end, we consider the symbol of gamma tilde underscore 1000w, which is given by omega 0 tensor omega 1 minus omega 2 tensor 2 pi I tau. The last entry of the second term here only depends on tau and not on w. Thus, we can use the first term here as a proxy for this one, and indeed define it to be the symbol of omega, symbol prime of omega 2. In this way, the symbol prime reduces the complicated identities of omega 2 to the previously discussed identities of omega 1 and 0 in a similar way that the original symbol reduces the identities of polylogs to the identities of the logarithm. Now let's look at a concrete example where this reveals some hidden simplicity and some nice structures that indeed allow us to bootstrap these. The example we look at is the 10-point elliptic double box integral, and here we have 10 massless momenta PA, and again we define dual momenta XA whose differences are the PA. Now, if we include appropriate numerator factors, the resulting integral only depends on 7 dual conformal cross ratios. This integral is the first elliptic contribution to planar n equals 4 sub Young-Mills theory. In particular, it's the only contribution to a particular component amplitude of the planar 10-point n cubed MHV. Now let's look at the symbol of this integral, normalized by omega 1 to make it pure, and by the 2 pi I, such that it has polylogarithmic degenerations without additional factors of pi. Now, applying all of the identities I told you about before, dramatic simplifications happen and a simple structure emerges. In particular, in the first two entries, the elliptic letters combine purely to logarithms of rational or algebraic functions of the dual conformal cross ratios. The same is mostly true also for the third entry, where then the last entry here is just the torus image of this kinematic function Cj, which is algebraic or rational of the dual conformal cross ratios. The exception is if the last entry is tau, then the third entry preceding it is a complicated linear combination involving in particular the omega 2s. However, if we apply the symbol prime to this, we see that we obtain essentially the same combination here, but in the opposite order. So in this sense, the symbol prime decomposes our symbol alphabet to just 53 logarithms, 6 simple elliptic integrals, and 2 pi I tau. Moreover, the symbol prime explains the occurrence of these omega 1s and manifests that the whole expression is double periodic and integrable with respect to tau in the last two entries. So the symbol prime ties these complicated functions to the simpler functions here. Now we can ask whether we can also bootstrap these elliptic polylogs or Feinman integrals, and as a warm-up, we can take our 10-point double box integral and ask whether we can disassemble it to individual symbol letters and reassemble it using a bootstrap. And the answer to this is positive. If we start with the first 7 letters occurring in the first entry and combine them with the 26 letters in the second entry, and now we impose integrability so that partial derivatives commute, and then impose Steinman, which Lance has just explained to you, we are down to 28 weight 2 symbols. If we combine them with the 53 third letters, we impose integrability and are down to 96 weight 3 symbols. And now if we combine them with the 6 last entries that aren't 2 pi I tau, we, after imposing integrability, obtain only one integrable symbol. Now here, in order to be able to ignore the 2 pi I tau as last entry, we use that the symbol prime ties these to the other 6 ones. To fix the last overall constant, we can, for example, use the differential equation that relates this double box to the 6D hexagon. This is, of course, very promising for bootstrapping also currently unknown Feinman integrals. Let me now come to a conclusion. In my talk, I told you about symbology of elliptic Feinman integrals and scattering amplitudes, where with symbology, I mean the knowledge how to manipulate these elliptic letters and find their identities that generalize log AB equals log A plus log B. I argued that for omega 1 and 0, these are given by Abel's addition theorem, and for omega 2, they are given by the elliptic block relations, which can be made manifest by defining a symbol prime. Applying this symbol prime to concrete examples, I've shown you how a simple structure is revealed. And finally, in a proof of principle, I've shown you how we can exploit this structure to bootstrap this 10-point integral. So far, we looked at simplifying this symbol, but it would, of course, be very interesting to lift also the simplified symbol to a simplified function. We are able to do so for simple examples, but it would be desirable to develop a more systematic approach. The next step would be to apply our technology that we just developed to bootstrap new elliptic Feinman integrals and scattering amplitudes that are previously unknown. In particular, this requires us to have a good guess for the elliptic symbol letters that occur in these cases. In ongoing work, we already understand how we can obtain the elliptic letters for this 10-point double box via a Schubert problem analysis. And we are now working on the previously unknown 12-point case, which is looking very promising so far. Finally, it would, of course, also be very interesting to generalize the symbology techniques from the case of the elliptic polylogs, which I told you about today, to the case where we have higher dimensional Calabi-Yau integrals. Thank you.
Thank you very much, Matthias, for a very clear talk. We have time for questions, please. Olli.
Yeah, thanks a lot for a beautiful talk, Matthias.
Thank you.
This is a question both to you and maybe also to everybody else in this room. It's quite intriguing for me to see that such an advanced example like 10-point double box only goes through omega 0, omega 1, omega 2, or not to the higher omegas. So what's the highest omega n that has ever been seen in an elliptic Feynman integral, let it be sunrise, banana, or other topologies?
So the reason we only see omega 2 here is because essentially of this differential equation. So this here is a polylog. This is the dx divided by y kernel. That way, if you write it as E4 functions, there's only ones and one 0. And then if you take the derivative to compute the symbol, you get only omega 2. But the highest omega I've so far seen, and maybe somebody in the audience can correct me, is on a poster outside where omega 4, I think, appeared in a differential equation in canonical form for the sunrise integral, now with a whole family of master integrals. But maybe somebody else can correct me, in particular the one that has the poster. There's a thumb up, so great.
Great, thanks a lot.
Okay, from what you said, is it correct that if I go to higher orders in epsilon for the same integral, I'll get higher and higher?
Yes, this is what I would expect, yes.
Okay. Yeah, more questions, yes.
Thanks for a nice talk, Matthias. So,
Thank you.
I think I just missed it. So this last entry condition that there's no 2 pi tau, does that also follow from the differential equation, or what's the origin of that?
So you're asking why we are able to ignore these 2 pi I tau. And the reason is that via the symbol prime, you can really tie the one that ends with 2 pi I tau to the other ones. So the symbol prime of the ones ending with tau is really the reversed order of the other ones. So we don't really need to consider them in the bootstrap if we assume that this structure holds also for the 12.1.
Okay. I don't see any other questions, so thank you very much, Matthias, again.
Thank you.
Okay, so our final talk today is by Dima Chicharin. He will tell us about null Wilson loop with Lagrangian insertion in n equals 4 super Young-Mills theory. Please.
Oh, thank you. Good morning. And first of all, I'm grateful to the organizers for the invitation to speak about this work with Johannes Henn. So I'm going to talk about light-like polygonal Wilson loop in maximally supersymmetric Young-Mills theory. As you will see, these observable in maximal supersymmetric Young-Mills theory coincide with an amplitude which we need for doing cross-section calculations. So this is a very nice feature of this observable. It's also, on its own, it also has nice symmetry properties and relation to geometry. So the motivation for this talk is related to precise collider physics. So to test our understanding of standard model, we need very precise theoretical predictions. Nowadays, we need to do collider calculation at next to leading order approximation. And in particular processes with 2-particle and 3-particle production are of great interest. And so in order to provide this prediction, we would like to be able to calculate QCD amplitudes analytically, and then we can use them to calculate cross-sections and event shapes. And divergences of QCD amplitudes are well understood. And so what we need to find a finite part of QCD amplitudes. But doing QCD calculations of QCD amplitudes is hard. That's why we need to find novel calculational techniques and the computational techniques, and N=4 super Young-Mills theory is an excellent theoretical laboratory where we can develop these tools and later on apply in calculations in QCD. But so here we develop tools and for amplitudes in N=4 and apply them to amplitudes in QCD. But can we say that amplitudes in N=4 are similar to QCD amplitudes? So now we are talking about finite parts of amplitude, and let's just count number of independent variables in both cases. So n-particle QCD amplitude depends on 3 and -11 variables. At the same time, amplitude in planar N=4 super Young-Mills depends on 3 and -15 variables. So this restriction in number of variables, it comes from dual superconformal symmetry of planar amplitudes in N=4. So let's substitute in this counting 4 particles. Then in QCD, we find that 4-particle amplitudes is just a function of one variable, dimensionless variable. At the same time, 4-particle planar amplitudes in super Young-Mills is completely fixed by dual superconformal symmetry. It's known BDS formula gives answer at any loop order. Similar in 5-particle case, QCD amplitudes are already very non-trivial. They depend on 4-dimensionless variables, and while QCD amplitudes are again given by BDS formula. And only starting from a 6-particle case, in N=4 we have non-trivial amplitudes, as Lance discussed in his talk. But QCD amplitude 6-particle, they are already way too complicated, and Johannes will say in his talk about progressing calculations of master integrals in 6-particle QCD. So, can we find an analog in N=4 super Young-Mills theory of a 4-particle planar QCD amplitude? So, and I'm going to motivate that indeed it's possible, and this is what we need. So here it's this f is ratio of 2 correlation functions. In denominator we have vacuum expectation value of light-like polygonal Wilson loop, and numerator the same Wilson loop, correlate of the same Wilson loop with Lagrangian, denoted by cross here. And this ratio, it's very similar to finite part of amplitudes in QCD. That is amplitudes where we divide out all divergences, all soft divergences. Okay, so what's nice about this ratio of these two correlation functions? Well, it's a finite observable in n equal 4 super-L, and it displays many nice properties. It has hidden symmetries, Youngian-like symmetries. It allows for Grassmannian representations, and it has nice geometric interpretations, relation to amplitude hedron geometry, and nice positivity properties. So, since we are going to discuss Wilson loop, let me again briefly recall you duality between a vacuum expectation value of polygonal Wilson loops and scattering amplitudes equal 4 in MHE configuration. It's the same as was in the talk of Lance this morning. So correspondence is given by this duality relation where when we replace momenta of scattered particles with differences of Cusp coordinates of edges. So we identify edges of Wilson loop with momenta of scattered particles. So both these objects are divergent, and so they need so we need to regularize them to evaluate them and to compare them. And so if we do this, then up to some details in the choice of regularization, so they coincide at weak coupling and strong coupling. But in this talk we'll mainly need another version of this duality, which you can say easier or maybe more, it looks more pure, duality at the level of integrands. So we compare four-dimensional integrants of Wilson loop and MHE amplitude, and they coincide. So, but before we go on to integrands, let me briefly recall some facts about divergences of Wilson loops. So divergences come from cusps, and they exponentiate, so that if when we take log of Wilson loop, we find that highest pole is just 1 epsilon squared, and it's determined by cusp anomalous dimension. So this, because of these divergences, Wilson loop has a natural conformal symmetry. In the context of amplitude, we usually call this conformal symmetry dual conformal symmetry, and this is what I'm going to do in this talk as well. This dual conformal symmetry acts on coordinates, and because of these divergences, Cusp divergences, this dual conformal symmetry is anomalous. So, but when we work with integrand four-dimensional, then dual conformal symmetry is exact. So how to define integrand of Wilson loop? In order to do it, we will rely on Lagrangian insertion formula. It says that if we take vacuum expectation value of Wilson loop and differentiate it in the coupling, then the result is this correlation function of Wilson loop and Lagrangian, where Lagrangian coordinate is integrated out. So there is a certain freedom here in the choice of Lagrangian. It will be convenient for us to choose a chiral form of Lagrangian. Well, how to understand this formula? Well, in order to do it, we can take path integral representation for Wilson loop, rescale all fields such that dependence on the coupling is only here, is a factor in front of action, and when we differentiate this formula in the coupling, we immediately obtain this correlator on the right-hand side. Okay, so let's apply Lagrangian insertion formula to generate integrands. So we take expansion of Wilson, weak coupling expansion of Wilson loop, substitute it in the Lagrangian insertion formula, and evaluate both sides at the lowest perturbative order. And then we immediately find that the one loop correction is this integral of this correlation function of Wilson loop and Lagrangian, which is evaluated at the lowest perturbative order. When we iterate this formula L times, we find L loop integrand. Again, it's given by correlation function of Wilson loop and L Lagrangians evaluated at the lowest order. Well, in the following, we are going to restrict this correlators to 4 dimension, then they are finite rational functions. Okay. In order to describe integrand of amplitude, we'll need dual coordinates. So x is dual coordinates for moment of scattered particles, and y is dual coordinates for loop integrations. Integrands of 4-dimensional integrands of amplitude are very well understood, and in principle they are known at any loop order, and also there are very explicit expressions for these loop integrands up to very high loop order. Okay, so then the duality states that the integrand of MHV amplitude coincides with integrand of Wilson loop, which is correlate evaluated at the lowest perturbative level. These two functions are rational functions, 4-dimensional, and also they have non-trivial chirality properties. Wilson loop itself is parity even, but we insert chiral Lagrangian, and due to this chiral insertion, this correlator has non-trivial chirality properties. Okay, so now we're ready to discuss this ratio f. So numerator and denominator, they both have divergences. Divergences come from cusps of Wilson loops, but in the ratio these divergences cancel out. So this ratio is finite in 4 dimensions. So how can we understand this f? So again, let's take a logarithm of Wilson loop and differentiate it in the coupling. Again, we apply a Lagrangian insertion formula and define that the result is f, where point x0 is a Lagrangian coordinate for Lagrangian, it is integrated out. F itself is a finite in 4 dimensions, but when we do integration over x0, it then defines a divergence 1 over epsilon squared pole, and coefficient at this pole is determined by Cusp anomalous dimension. This is what we saw before, that Cusp divergences of Wilson loop, they exponentiate. So let's look at this relation in more details. Since we can construct integrands of Wilson loop, we can also construct integrands of logarithm of Wilson loop, which I denote here with omega. And this omega, it has nice properties. Indeed, when we integrate out in this L+1 loop omega L coordinates, then we find that the result is finite. Usually when we do one loop integration in integrand of Wilson loop, then we immediately encounter divergence. But here we can do L integrations and in 4 dimensions, and the result is finite. So when we do these, integrate all but one loop variables, then we find finite results. We can do all these integrations in 4 dimensions. In other words, if we take L+1 loop integrand of logarithm of Wilson loop and freeze one of loop integrations, then we get immediately a loop f. Okay, so previously we saw several correlators, so let's compare them. Here we have vacuum expectation value of Wilson loop, and here integrand of Wilson loop. This is MHV amplitude, and this is integrand of MHV amplitude. And f, it interpolates between the two. And what is nice that it shares all attractive properties of both of these objects. So it is a finite in 4 dimensions like integrand, and it has exact dual conformal symmetry like integrand. But integrand is just a rational function, and the number of variables changes with loop order, it increases. But this f, it's a transcendental function, so it's already interesting. It's much more non-trivial than the integrand, and number of variables is fixed. It doesn't change with loop order. So as you can see, it's very similar to finite part of QCD amplitudes, and number of independent variables is the same as for QCD amplitudes. Okay, so let's consider perturbative expansion in tweak coupling of these f. So Born level, one loop, two loop, and so on. He's typical. Typical Feinman diagrams, which we would need to calculate if we calculated in perturbation theory. And the expansion of a loop correction is similar to a representation for a loop correction is similar to amplitude. We decompose it in leading singularities, which are rational algebraic function of coordinates, and they carry non-trivial dual conformal weight at Lagrangian point like 0, and they are multiplied by transcendental function of dual conformal cross ratios. So immediately we can ask many interesting questions. What are these leading? What are these leading singularities, and which transcendental functions we need to describe and point observable? But before we do this, let's do one more trick. We have a point x0 and we have dual conformal symmetry. We can sacrifice dual conformal symmetry by choosing a special value for x0. It will be convenient for us to send x0 to infinity. By doing this, we don't lose any information. What we do, we just switch to a frame. To a particular frame. So when we do this, of course, we lose dual conformal symmetry. But now, what is nice, that we have here in this lowercase f only dependence on cusps of a contour, and it's the same as dependence on n light-like momenta which satisfy momentum conservation. And this function f, it doesn't have dual conformal symmetry anymore, just Lorentz invariant function. So, and it is defined in 4 dimensions. So as you can see, it's a kinematic of n particle scattering in massless QFT. So this f is very similar to finite part of QCD amplitudes. So in order to gain some experience with this observable, well, it's useful to take a look at some perturbative data. And the Cusp case, it is known up to 3-loop order, and it's also known in the leading order, it's strong coupling. And recently it was studied in a negative geometry context, and all loop tripat was calculated, and this captures a contribution from any loop order. Okay, then at N-Cusp case, it is, this observable is known at 1 loop, calculated recently, and in a 5-Cusp case, we were able to calculate it up to 2-loop order. Okay, so what we can say about 4-Cusp case? It's kinematic of 4-particle scattering, which we can describe by 2 Mandelstam variables, S-channel and the T-channel variable. In this case, there is only one leading singularity, which is in the frame x0 to infinity just S times T. And loop corrections are described by a transcendental function of one variable, this ratio T over S. And these functions, they are a harmonic polylogarithm, which Lance reviewed in his talk. Well, perturbative results, Born level and 1 loop are simple, but starting from 2-loop expressions are more complicated. So here we have only one leading singularity and transcendental function of one variable. But in 5-Cusp case, it becomes much more interesting. We did a perturbative calculation up to 2-loop order, and we find the 6 leading singularities. And the transcendental function, which describe loop corrections, they depend on 4 cross ratios. In the frame x0 to infinity, they are 4 ratios of 5 biparticle adjacent Mandelstam invariants. So it's this formula is very similar to what we would encounter if we calculate finite part of a QCD amplitude. Also, in the 5-Cusp case, we have non-trivial parity properties. We have 4 independent light-like momenta, and we can cook up parity or the Lorentz invariant. And all these leading singularities and these transcendental functions, they have non-trivial parity properties. This is a typical feature of five-particle scattering. And indeed, this is what we find for these observable. So what can we observe about Legian singularities? Well, it's very instructive to multiply them with 5-point Parquet-Taylor prefactors so that they gain non-trivial helicity weight. And here I write them using spinor helicity notation, using spinor helicity brackets. So what is nice about this formula that they invariant under conformal symmetry, but this time it's conformal symmetry in momentum space. So the dual conformal generator is second order differential operator in momentum variables, and acting on these expressions, it's easy to see that it annihilates all of them. It's annihilated for trivial reason. It's differentiating in lambda, lambda twiddle, and lambda twiddle never appear simultaneously in each of these expressions. Okay, so this conformal symmetry is a hidden, we can say that it's a hidden symmetry. So dual conformal symmetry of this capital F5 with X0 dependence, it's expected, but conformal symmetry of leading singularities was not expected at all. Okay, so what about loop corrections? So leading singularity have nice properties, they're conformal. What can we say about loop corrections? To describe loop corrections, we need so-called pentagon functions. These are functions which we need to do calculations of five-particle QCD amplitudes. So here we are restricted to two-loop order, so we need pentagon functions up to weight 4. These pentagon functions, they are polylogarithmic type. They can be defined as iterated integrals built upon 26-letter planar pentagon alphabet. Here are letters of these alphabets. So as you can see, some of the letters are quite complicated. So it's very nice that to do this calculation n equal 4, we need these cutting-edge results from perturbative QCD calculation. So we need this function, and we evaluate, to evaluate these functions, we have to apply some numerical routines for the evaluation, the same as we need for doing NNLO calculations in QCD. Okay, so let's, which nice observation can we do about all of these loop corrections? So, as I said, there is a relation to amplitude-hedron geometry. We can ask question, what about positivity properties of the integrated results? It was observed that in the one-loop amplitude-hedron region, in four-particle case, this observable has definite properties. But here, this is positivity properties or negativity of loop corrections is well, they come from properties of this function of one variable. But in the five-particle situation, we observe the same positivity properties, but here they much more non-trivial. So the sign of loop corrections changes with the loop order. It alternates with the loop order, and so it is in this one-loop amplitude-hedron region, this sign of 5 is fixed. So what's indeed here non-trivial, that here we have expression for F5 as a sum of 6 terms, and these G's are transcendental functions, some combination of pentagon functions, which we can, the best we can do now, represent them as one full integral and use some numerical codes to evaluate them. So what we observe, that sign of individual term, it varies inside the amplitude-hedron region, but the sum always has a definite sign as here. So it can be an indication that there is a more natural way to rewrite this observable F5, but right now it's very non-trivial. Well, I don't have much time, so as I promised, there is a nice connection to amplitudes. expectation value of Wilson loop are dual to amplitudes and MHV and equal for super-Young-Mills, and our observable it's dual to amplitude all plus and pure Young-Mills. So here we are talking about all plus amplitudes in planar limit, single trace contribution. At tree level they vanish, at one loop they are rational function, and at two loop order they are transcendental function of weight 2, and so on. So there is a drop in transcendental weight by 2. So there is a number of perturbative results for all plus amplitude. And particle amplitude is known at 2-loop order, and 4-particle amplitude is known at 3-loop order. Okay, so this is the duality relation. So how to interpret it? At the lowest order, it means that if we take one loop all plus amplitude, which is a rational function, and compare it with our observable f multiplied by endpoint particular prefactor, then these two rational functions coincide. At two loop, beyond leading order, this relation is as follows. So here we compare quantities, four-dimensional quantities, and only their leading transcendentality piece. So finite part of Young-Mills all plus amplitude is given by this logarithm of finite part of MHV amplitude and this ratio, that is this ratio f. Okay, so this duality relation says that a loop Lagrangian insertion is equivalent to leading transcendentality weight with L plus 1 loop all plus amplitude in Young-Mills. And it's much easier to calculate a loop Lagrangian insertion. So we find a perfect agreement with available perturbative data for all plus amplitude. And also we can make predictions for all plus amplitude, of course in planar limit and maximal transcendentality part. We can make predictions for 3-loop 5-particle all plus and 4-loop 4-particle all plus. Okay, so these nice properties, they don't stop at 5-particle case, and particle case we have a conjecture for leading singularities, and we also observe similar pattern with symmetries, with conformal symmetry and conformal non-conformal symmetry. They combine together in Youngian-like relations for these leading singularities. Okay, so here are conclusions. So we discussed this Lagrangian insertion, and we saw that they are very similar to massless, finite part of massless QCD amplitudes, and moreover, they just exactly coincide with all plus amplitudes. They have nice positivity properties and very intriguing conformal and Youngian symmetries. Thank you.
Thank you very much, Dima, for a beautiful talk. We have time for a couple of questions. Yes? Yeah, no.
Thanks a lot for a great talk. Can I ask you, did you think about calculating the Wilson loop with 2 Lagrangian insertions or more, like going away from your special object F?
Yes, we thought about it. Yeah, it's very interesting. Well, I didn't put any outlook here. There are numerous questions which we can ask. So here we consider bosonic observable, but we also studied supersymmetric extension. So dual superconformal symmetries, they are also very interesting, and Youngian in this case as well. So now our question is, we can put more Lagrangians, still we have several Lagrangians, then still we have finite observable, and so it would be interesting to study it.
Thanks for that great talk. Duality there is pretty fascinating. In the one loop all plus, there was this connection that the integrands looked like the n equals 4 integrands, but with an extra factor of the extra dimensional momentum. But I don't know if you see anything like that in the way you do it.
Yes, I'm aware about these results of yours and your collaborators. There is extension of this relation at also at two-loop order, but we don't see immediate explanation of this observation on the integrants with this relation, because here we compare already integrated quantities. And we expect that it works at any loop order, but for integrants at each loop order you need to modify. I know that at two loop order there was some extra modification, so it was easy. It was at two loop order it's more complicated than at one loop order, and at higher loop orders I expect that it became more and more complicated.
Can I ask one more question? Do you expect the pentagon functions to be sufficient at higher loop order than 2?
We hope so. So it's if we yes, we hope so, and we hope that we can use a bootstrap approach to study this observable beyond two loops, because right now at two loop order we use a perturbative calculation. We write down Feinman integrals, reduce them to master integrals, and it's like a calculation of QCD amplitudes, but it would be interesting if we can do it without Feinman integrals.
Okay. I don't see any. Is there any more question? Okay. So thank you very much. Okay, now it's a coffee break.
Please, do you hear me, Mr. Wen?
Hello.
Hello, here's a technician from the conference from Prague. Do you hear me well, please?
Yes, I can hear you.
Yeah, voice from you, it's also well, also good. So please try to share your presentation.
Okay, let me see. Right.
Yes, and then make it full screen, please.
Just a minute. I probably need to share again.
Yeah, it's perfect. So you are last in this section, so please listen to the conference and be ready. Or you can keep it like this if you don't mind.
You may keep this screen.
Okay.
No, I'm asking. Maybe I should just stop the share. I will share later.
Okay, but the test is okay, so for now that's all, and the chairman will ask you to start as the last in this section. Thank you.
Okay, thank you.
Okay, good. And it looked like Yara explained all the technology, right? So the microphone's over here and... I think so, yes. Will be when you're talking, I guess. They handle them. Great.
Is there a screen where I can see?
Yeah, I think probably on that one. If you need to, sure.
Sorry?
Oh, yeah, sure.
Yeah, if you don't mind. Okay, before everybody is in the room, I will make a short announcement or two. So we have, unfortunately, we have first COVID case, but the person was yesterday was negative and using the mask and everything, and only today the test went positive. So I think it was not that strong yesterday. The person was among us, so I hope it will not spread. Another announcement, there is a free afternoon, and there was already a question concerning possibility to use rooms. Also yesterday, some of you used the room, so please come to me, and I think we can still use there is a really nice room if you need for a discussion upstairs, and I guess we can use it also today. Yeah, and I think that's it.
Great. Well, now I think we can begin the second session of this morning. And to start us off, we have Johannes Henn, who will be giving us a first look at the function space for 6-particle amplitudes in QCD. So go ahead.
Thanks a lot. It's a real pleasure to be at this wonderful conference and in this beautiful town. So this talk is based on 2 works, one which already appeared with these collaborators, and a second one which is in the pipeline together with Antonella and Julian, who are here at this conference as well. So we heard already a lot about the fantastic progress in Feinman integral calculations that then enabled next to leading order phenomenology. In particular, we heard yesterday from Simone Zoya about this. In this talk, I'll try to go one step further as the number of legs. So we'll have a first look at 2 to 4 integrals. But of course, this is much less developed, so we're very far away from anything like drawing experimental plots. It will be more like a first theoretical investigation. And there's several motivations for this. So on the longer time scale, of course, with a lot of extra work, this will eventually lead to, you can do with this describe 4-jet processes. But also there's more theoretical questions, such as we all know that there's wonderful things happening for the function space in n equals 4 Swing mills. And one can ask, which of these wonderful properties actually also carry over to QCD? And if you think about what we've heard about, for instance, for the 5-particle function space in QCD, well, it depends on a lot more variables than we're used to in n equals 4. So there's kind of a shift. Things get more complicated already with lower number of particles. But if you ask me, if you look at the types of iterated integrals we get and the types of analytic structure that we can discuss, it's just very beautiful as well. And in fact, the previous speaker just made a connection between that function space which we use in QCD and some Wilson loops of Lagrangian insertions in n equals 4 Swing mills. So I think this progress goes hand in hand, and that's one more reason for me to try to figure out what can we find at 6 particles in the general case in QCD. So this talk will be in 2 parts. So in the first part, I'll talk actually about 1-loop integrals, and we'll have a fresh look at this, looking in particular what happens when we compute in general D dimensions. So something that's required if you want to do conventional dimensional regularization, for example. And that will give us an idea of what to expect also at higher loops if we wanted to do that. And then the second part, this is the paper I mentioned. We look at, we have a first look at what happens at 2 loops, and we look at the genuine 6-particle 2-loop planar integrals and investigate them on the maximal cut. And then I'll discuss the results and give some outlook. So let's first talk about the kinematics. So if we're in general d dimensions, it's actually quite easy to count the number of invariants that a scattering amplitude should depend on. So basically you have this number of kinematic variables, and you notice it's quadratic in n. There's a useful way of labeling them, which is depicted here. So if you arrange the momenta in a polygon, it's a closed polygon because of momentum conservation, then the diagonals can be used to indicate Lorentz and Poincaré invariants. So, for example, this xi minus xj squared corresponds to sum of all the momenta on the left, or equivalently, because of momentum conservation, to those on the right. And in the case of 6 particles, which is of interest to us, this means that we have 9-dimensional variables. And so in more standard momentum space notation, you can choose those 9 variables as a basis. Now, you might remember accounting from the previous talk, which is a bit different. So how can that be? Well, things change when we take the external states to be 4-dimensional. And in this case, there's actually, the general formula is 3n minus 10 invariants. And, but if we stick to 6 particles, that means that there's 8 independent variables. So actually, these 9 variables were not independent. And the reason is that we can write down a vanishing Gram determinant. So essentially, you have that 5 external momenta in 4 dimensions, they are linearly dependent. And that results in this constraint. So these are the 2 scenarios we can look at. If you want to be in 4 dimensions, for example, you may want to solve this constraint by using momentum twistor variables. So for the first part of the talk, I'll be assuming that we take the external states to be d-dimensional, and therefore we'll have functions of 9 dimensionful variables, or equivalently 8 dimensionless variables. So the main method we'll be using to investigate the functions is the differential equation method. You've seen that already from in a number of talks yesterday. So the main idea is that eventually we'll put the integrals that we are interested in, the so-called master integrals, into some vector, which is f. It has n components, where n depends on the problem. And then the claim is that the right-hand side of the differential equation, so d varies the function with respect to all of the kinematic variables. The right-hand side is supposed to take this form, where there's some constant n by n matrices which multiply what we call the alphabet. So that's what we heard about this morning from Lance, and also yesterday from Song He. And one of my main motivations is to ask, what is this alphabet in the 6-particle case? I should also mention, we've heard about this from Matthias, that this is true for certain classes of multiple polylogarithmic functions, and then in the case of elliptic and more complicated functions, you expect this right-hand side to take another form, where in particular there's an open question, what replaces this d log, and what should be the general form of the right-hand side. I think that's very interesting, and there's a lot of research ongoing on that question. So just to give you an idea of the state of the art, now staying within polylogarithmic case, I just have a few examples, more or less random. So there's these 2-loop non-planar integrals where you have 2 massive external legs, which is useful for massive vector boson production. This dates back to 2014. So just to give you an idea, referring to the numbers in the equation on the previous slide, there the number of master integrals n was 51. We had 3 dimensionless variables, and the number of letters, so which encode the analytic structure, is 19. Somewhat more complicated. So this is ordered somehow by complexity. Just a couple of years ago, we completed these non-planar 2-to-2 massless integrals at 3 loops. So there, since we had 4 particles, there's only one dimensionless variable, but there's more master integrals because it's a higher loop problem, and there's actually just two alphabet letters. And very recently, we heard about this from Simone. The 5-point two-loop integrals of one off-shell leg were evaluated, all the planar ones and most of the non-planar ones, by this collaboration. And so this is a good example of where the state of the art is now. So here we have 135 letters, 5 dimensionless variables, and 63 alphabet letters. So let me now proceed to the first part where we discuss the one-loop hexagon in d dimensions. So you might say, well, what's actually new about this? Because there's actually been some previous work on this integral back in 2011. So in fact, the integral in exactly d equals 6 dimensions, it's a wonderful function. It's related to functions we heard about this morning by Lance. And it was computed analytically. And there's lots of stories. For example, there's a relation to an A3 cluster algebra. We've heard about antipodal duality and a lot more, but it's another story and not for this talk. So instead, we're going to consider this in dimensional regularization. So if you wish, in 6 minus 2 epsilon dimensions. And there suddenly it's a lot more complicated. So as we saw earlier, we have then 8 dimensionless variables. And what we are after is to look at these higher order terms in the epsilon expansion. Because that's what's needed if you wanted to compute this in conventional dimensional regularization, and then, for instance, feed it into some two-loop calculation, where it effectively will multiply some counter term. And then therefore, even though we're talking about higher order terms in the epsilon expansion, they become relevant and they contribute to the finite parts at 2 loops. Or said in another way, you can use this information to study scheme dependence of your calculation. So it enables you to control how your calculation varies when you want to switch from one scheme to another. So we follow the conventional approach. We first have to figure out what is a basis of master integrals in this differential equation method. So essentially draw the diagram and all of its subdiagrams. You can run some computer program to tell you how many of them are relevant. The answer is 33, so n equals 33 in our case. And now the next question is, how do we choose a good basis such that we have this nice form of the differential equations? And this is very well studied, in particular at one loop. There's basically a roadmap how you can do this. And concretely, actually, Spradlin and Volovich, they studied n-gons and n-1 gons in n dimensions. And the upshot is that those integrals are actually they're uniform weight functions if you normalize them by their leading singularity. So there's a very simple prescription for what basis integrals we should choose. Now, strictly speaking, this was done in integer dimensions, but we'll use that as a working hypothesis to start out. So you might wonder, well, now if we have the hexagon close to 6 dimensions, the box close to 4 dimensions, and well, I don't know, the triangle close to 4 dimensions, how does that make sense? We'd like to write differential equations where everyone is on the same footing, or rather in the same dimension. Well, there's a technical trick which allows us to achieve this. In fact, there's dimensional shift relations. So we can always shift the dimension by plus minus 2. So we use this trick, this insight from Spradlin-Volovich, and then shift by 2 and can write all the integrals in the same dimension formally. And so this allows us to find the canonical differential equations. And so at that stage, we're happy. We can read off what the alphabet is, and we can analyze the function space. So let me give you a little bit of information on that. So it turns out that there's 103 alphabet letters. You can group them according to parity. Most of them were previously known because they depend on some subsectors of pentagons and lower integrals. And there's 10 new alphabet letters which have to do how this hexagon couples in particular to the pentagon and then through the pentagons to the lower integrals. there's two types of square roots which we encounter, which have to do with these diagrams depicted here. So essentially you get certain square roots when you consider the leading singularity of those integrals. And they then feed into the alphabet. So the upshot is that we have 103 alphabet letters which depend on the 8 dimensionless variables and they involve algebraic functions which in particular have certain square roots. Now, for the experts, when you have a differential equation, you need to fix the boundary condition or have to provide some boundary information. So this is also rather well understood, and I'll try to explain it with this cartoon here. So if you think of the kinematic space as this plane here, and typically we want to look at some kinematic region which are denoted by R. So this could, for instance, be the Euclidean region. So we have this, and then usually consider a reference point, which is this dot I here. So what you'd like is you have first order differential equations. To fully specify them, you need the boundary value at one kinematic point. That's sufficient. So how do we get that? Now, if we look at the alphabet letters, they have singularities. And these singularities, they correspond to certain hypersurfaces, which I've indicated by these dotted lines here. Now, there will be various of these hypersurfaces, and for physical reasons, you sometimes know that the function should actually be non-singular at those hypersurfaces. So in other words, these correspond to spurious singularities. And so then what we do is we travel from our reference point to one of these hypersurfaces, like for instance, let's take this path here, and we impose regularity on this line. Concretely, what we do is we have this nine variable space. We parameterize a slice dependent on some parameter x. So then we see that the alphabet actually reduces enormously to just this four-letter alphabet. And so x equals 0 in the alphabet just corresponds to a reference point. So we first make sure that that's actually well defined. And then, for instance, if we travel over here, this line number 2, it could correspond to the singularity x equals 1. And then we make sure that the functions are regular there, and so on. And so actually it turns out that in this problem, just using this one path is completely sufficient to fix the boundary information. If you have more complicated problems, sometimes, as in the cartoon, you need to consider different slices to fix everything. So, having done that, we have the first order differential equations, we have a boundary value, so then we're in complete control of the function, and we can write down some iterated integral representation that then is ready for numerical evaluation. So that's what I'd just like to illustrate briefly. So here's some table with some more or less random reference points. So we see here we have these two kinetic points. There's some values. I think they're imaginary because of the leading singularities that we factored out. So we validated this against some programs on the market, and they agree with these, the digits shown there. Maybe one thing to highlight, because our setup is general, we can choose kinematic points which are valid for d-dimensional external states, like here, so they do not live on this Gram determinant surface, or of course we can choose to go onto that surface, which would correspond to 4-dimensional external states. So just to wrap up this part, so we have now the full d-dimensional one-loop hexagon alphabet, and we found two new letters that appear there, as compared to the 4-dimensional helicity scheme. And then we focused on the weight 4 part of the hexagon, which is the first new term, which we'd expect to contribute at order epsilon squared, or at weight 4 to some one-loop amplitudes. And we very much look forward to actually integrand expression for these full amplitudes that were reported on by Alex Edison, where we could then use our analytic formula. So Now let me switch gears and go to two loops. So there, we've heard in previous talks that essentially we know everything up to the 5-point case. So therefore, really the most interesting is to look at the genuine 6-point Feinman integrals. And by genuine, I mean that you have the external momenta flowing in such that they never flow into a corner together, because that would correspond to a 5-particle subspace of kinematics. So let me just see. Okay, I'll have in a minute a picture of all the relevant diagrams. But here I'd just like to make one point, now to compare what's the difference between this d-dimensional, between treating the external states in d dimensions and in 4 dimensions. And so it turns out it already makes a difference in the number of functions that you need to consider. So for example, for this sector here, so if we go to maximal cut, for d-dimensional external states, there's 7 master integrals, while for 4-dimensional external states, there's only 5 master integrals. So you see that there's already a big difference. Now, eventually we'd be interested to know what the answer is in the full d-dimensional case, but given the fact that, as you'll see, these calculations are enormously complicated, for this first work, we restricted ourselves to the 4-dimensional helicity scheme. And so we're working from now on with this case. So here's the list of the genuine sectors. So you see that in a way this is the most complicated diagram in the sense that it has most propagators, but there's also a pretty complicated double box which has in this sector seven master integrals. So now in view of time, I'll just focus on explaining how things work for this double pentagon integral. So actually, there's some information available to us, because in fact, in around 2010, 2011, some of these double pentagon integrals were considered in the context of n equals 4 Swingmills. And there's beautiful work by Nima and collaborators who constructed finite uniform weight integrals, and they're depicted up here, where these lines, they correspond to some numerators. And in fact, those integrals were also computed analytically. However, now this is not enough for what we're after, so you can already get a hint from this by comparing the numbers. I just told you that we need 5 master integrals, but there's just 2 pictures, so that doesn't quite match. So we actually need more basis integrals, and not just any basis integrals, but integrals that have this uniform weight property. And secondly, this is perhaps more technical, but very important, these definitions contain 4-dimensional numerators, and we have to lift their definition to d dimensions because the loop momenta are d-dimensional. So that raises some questions and makes some choices will be necessary. So how do we deal with those problems? So first, we can add now, we have some new integrals which we can add into the basis. And in particular, the first point has to do with dimensional shifts dimensions. So we can allow ourselves to consider 6-dimensional integrals and then shift them to 4 dimensions. And this turns out gives us some new elements. Closely related to this, we can write evanescent numerator terms. So for example, Gram determinants, which depend on the loop momentum, but vanish if the loop momentum were to be taken 4-dimensional, as in this previous works. So this gives us a few more things to play with. And then for the second point, how to choose a good basis, there's some analysis which essentially extends the analysis of 4-dimensional leading singularities to include a little bit more of d-dimensional terms. And that'll allow us to just get enough information that's sufficient for finding our basis. So here's the technical slide. I hope it's not too technical. Where you see how these integrals from Nima and friends were defined. So you have a loop momenta L1 and L2, and you also define some complex vectors. So they depend on the external kinematics. So this is all written in some 4-dimensional spinor notation. And then essentially, you see here you have these numerator terms L minus W squared, L minus V squared, which correspond to these numerator lines. So this is our starting point. That's a 4-dimensional starting point. But it's not enough. But we can kind of play with that. And here's the upshot. So here's a list of 5 uniform weight master integrals that we find. So first what we see is that we can take parity odd combinations of the numerators from the previous slides. And these turn out to be perfect. Then we have a third integral where there's a mu here. So this is one of these evanescent numerators I was mentioning. So this clearly, it would just be 0 in 4 dimensions. The fourth integral is the scalar integral in 6 dimensions. Also pretty simple. And then finally, for the fifth integral, we take the parity even combination of 2 of the objects on the previous slide. But this, it turns out we need to modify it a little bit. So here we have to modify something proportional to this evanescent term and a certain polynomial f5. So you see already it wasn't completely trivial to find this. But with this choice, then we end up having a canonical form. So what does it mean? So we considered the differential equations on the cut, which means if you look at the full system of differential equations for the full family of integrals, what we considered were the diagonal blocks here in red, which correspond to these genuine 6-point integrals. In blue here are then all the subsectors with 5-particle integrals. They're already known. And so what's still left, and this is for future work, are these blocks in gray. These are the off-diagonal blocks which link the genuine 6-particle integrals to the pentagon integrals. So now, like at one loop, just some numbers. There's pretty much there's a lot of alphabet letters. So just in these cut sectors, we have 205 letters with various square roots. So in view of time, I won't say much more about this. So let me come to the discussion. So I showed you the d-dimensional function space at one loop, and so this integral, the hexagon integrals, is now known in conventional dimensional organization. And then in the second part, I showed you the genuine 2-loop planar integrals on the maximal cut. We had to do a little bit of work to shift the master integrals from the 4-dimensional definition to genuine d-dimensional ones, but this was possible, and so this allowed us to define new alphabet letters. So what we'd like to do in the future, of course, is to complete these off-diagonal terms, which would then give us the full alphabet and also allow us to use these integrals for in specific amplitudes or other observables. Just a few more words on the outlook. So really the goal, at least my main motivation, is to identify this full 6-particle alphabet. I also would like to mention that this goes hand in hand, or is closely related to another problem, that if you go to observables, these transcendental functions will come with certain coefficients, algebraic or rational coefficients, which is in a way is another bottleneck in calculations. And it's closely related because they share the alphabet, and these factors, they share a singularity structure. So that would be also very interesting to investigate. And as a last point, I'd like to come back to what I said in the beginning. And once we have those functions, we have that data that we can play with and ask more questions. Do we see any of the miracles that also appear in n=4 supermills? For example, which of these functions which we could theoretically write down do actually appear in the amplitudes? So for example, what about the analyticity structure, Steinman relation, and so on? And finally, to connect the 2 points, the transcendental functions, they typically have singularities and zeros, and they're linked very closely to the rational factors. So one can then also investigate how the two appear together. So I think there's a lot of things to do. As you can see from the numbers, it's kind of one order of magnitude up from what we're seeing at 5 particles. But I think it's certainly something that will be very interesting for the future. So I'll stop there.
All right, any questions for Johannes? We've got
Thanks for the talk. Maybe you've said this and I missed it, but are you considering any particular helicity configuration, or is this for all of them at once?
Yeah, thanks for the question. So this is really establishing what the function space is. So in this method of differential equations, one really, in a way, one considers all the possible functions that could appear, and then this is very flexible. It could be used for any helicity process that you wish. So it really, in that sense, it really establishes a basis. Once this calculation is complete, we have full control. We know what the worst functions, so to speak, are that could appear in any planar two-loop six-particle process.
Thank you.
Hi, Johannes. Thanks for the nice talk. So I wanted to ask a little about your alphabet. So for the even letters, did you investigate how they act under soft limits? For example, can you represent them neatly using these trace plus objects?
Right. Yeah, thanks for the question. So I think the question of the alphabet letters is better understood at one loop, where I think there's some nice representations in terms of traces, and let me say in this way, there's some cases, in particular the five-particle case, where I know that there's very beautiful representations of the alphabet letters. For example, where you see certain linearity in the momenta, and so you ask about soft limits or shifting a momentum. So for example, in the five-particle case, it's possible to write the alphabet such that you can see that under, for instance, a BCFW shift, they're linear in the shift parameter, which I think is quite beautiful. So this is certainly something we'd be looking for here. To be honest, in particular, the two-loop case is so complicated that we simply haven't had enough time probably to look in more detail at the alphabet letters. So there's also an interesting question to, once you have the alphabet, to try to see if it has some further structure, if it's naturally written. So we like typically, let me just show this. Yeah, we like typically some ratios where this F4, if it's a square root, that you write a square root plus or minus something rational. This makes the parity property manifest. But also often, and this is what I was just referring to in my answer, it's very nice to write traces like this, because this can highlight some linearity property in the momenta. Short answer is I don't know yet the final story at two loops and six particles.
So if I can just ask a speculative question, do you have any feeling for whether or not all of these letters are going to be turning up in the finite remainder when the amplitude is eventually computed?
Yeah, that's a great question. Thanks for asking that. So I have a very clear feeling. It's also a little bit based on evidence. So in all the cases that we've looked at, in particular at five particles, it's the case that once you go to the finite remainder, certain alphabet letters drop out. You have additional nice properties. So for example, in the five-particle alphabet that Simone was showing, the letter 31, it just disappears from the answer. And depending on who you ask, there's also some cluster alphabet, I mean, it feels natural from some cluster alphabet viewpoint. So absolutely. So when I quote these crazy numbers, and 205 is not yet the final one, because one also has to include all the subsector and off-diagonal ones, there will be some interesting numerology and finding out which part of the letters actually appear, say, in some finite remainder at two loops for those weight four functions.
Thanks.
Let's hear from Yaroslav.
I wanted to ask on the upgrade of the 4D numerators to D-dimensional numerators. So in the double pentagon example that you showed, you used the 4D numerators, but that there was some work to be done in addition. So I just wanted to ask how canonical is the operation, or how easy it is?
Yeah, thanks for the question. And maybe I should say, if it came across as too harsh, so there's nothing wrong at all with these beautiful numerators that you wrote. There's rather a choice, because the numerators that do their job in 4 dimensions for 4-dimensional loop variables, and that's what they were designed to do. However, then they're written then naturally in this spinor helicity language, or in momentum twisters in your paper, and this just leaves open what is a good, there's no unique definition beyond 4 dimensions, so then it's up to us to choose. And so the thing that's not working perfectly in a way is our interpretation of how we should lift them to D dimensions, and then we have to put in some work to fix it. So I wanted to clarify that, just to be sure. How unique is it? We try, of course, to save some work. So it's very easy to do the four-dimensional cut analysis. This gives the four-dimensional part. And now, doing a completely d-dimensional cut analysis is difficult. You can do it sometimes nicely if you have scalar integrals, like here with scalar six-dimensional double pentagon. But beyond that, we try to just keep a little bit of extra information. And I would say it's certainly not at the stage where it's algorithmic, but it's a little bit of trial and error. And we try to just keep, you know, enough extra information, looking a bit beyond 4 dimensions to solve the job. But I think there's also a number of people working on this. There's a few other papers where there's kind of more experience being gathered on how this works.
And I believe we had a question from online. Can you just remind me? Yes. So this is a question: in the evaluation of the master integrals at one loop, how smooth is the transition when going onto the vanishing of the grand determinant constraint? And
right. Okay. Yeah. Great. Yeah, that's a great question. Let me go. I don't have the. Let me. This is a two-loop slide, but I think it illustrates a little bit. So the analog at one loop is that we have this hexagon here in red, and then we have all the subsectors in blue. Now the question is, what happens when we go from this 9-dimensional parameter space and we impose the Gram constraint? Is that a smooth limit or not? The answer is it's not a smooth limit. It's actually extremely interesting. I'm trying to address the camera, the online questioner. So it's very interesting. So at the level of a differential equation, it turns out that in particular in this off-diagonal block here, you have certain alphabet letters, and in particular the new alphabet letters, that become singular as this Gram determinant vanishes. And so then what happens? I mean, does the method break down? No. One has to remember that this matrix, it multiplies the vector of basis integrals. And so we're kind of always assuming that when we say it's a basis, that it means that the elements are independent. However, once we use the Gram determinant constraint, then we expect a relationship between hexagon integrals and pentagon integrals. And so the potential divergence here is then balanced by a zero that appears so there's a relation between the master integrals. It's quite subtle, and to be honest, we're still working on fully understanding some details of this relationship, but this is how it's going to work.
Thanks. So in view of time, I think we should start moving on to the next talk, so let's thank Johannes again. And so next up, we have Matthew Schwartz, who will be telling us about machine learning for amplitudes.
Thanks. It's great to be here. This is my first Amplitudes conference, and I'd like to thank the organizers for giving me the opportunity to speak to you. This talk will be very different from the rest of the talks at the conference. It'll be a little bit more philosophical, a little bit short on technical details. You know, it won't all be apocalyptic prophecies about robots taking over the world. There'll be a little of that. But mostly, it's meant to be inspirational in that I'll present some problem that we use machine learning to address that's relevant to this community. But more generally, there's a lot of other similar problems. And I'd like you to think about this not as this particular problem is so interesting, but as an example of the kinds of things that machine learning can do. And think about in your own research what the possible applications are, because I believe this area is going to grow and grow. And we'll see what happens. So to begin, let me give you some context of how I came into this area. So my background, well, for some time I worked on jet substructure, which is asking questions like, how do you find the top quark that decays to hadrons at the LHC? And the approach that we took, you know, around 15 years ago was you study how the particles decay. So here's a top, it decays to 3 quarks, and then you recluster them back into the jet and so on. You think about it, and you think about the physics, you think about the helicity angle and the W within the top and so on, and you figure out a way to find these boosted tops over backgrounds of jets, QCD jets. And this result we had here was this operating point here, which is some measure of how well it does. And it doesn't really matter what's plotted here. The point is that higher is better, so kind of draw horizontal lines. This was the state of the art in 2008. About 6 years later, the state of the art moved up here. And if you draw a horizontal line, you see that there's there's a little bit of improvement after a lot of hard work. And then what happened is around 2017, machine learning took off, and then we started getting these curves like this. And this is, the best one here is this point cloud, which is modeled off of some Google network, that just blows all of these old traditional methods out of the water. And so basically what happened was, essentially overnight, machine learning destroyed a whole field of physics, which was this sort of physics-inspired collider physics. And now all of that collider physics is done with machine learning, and nobody tries to think about the physics anymore. And this is both good and bad. It's bad because you lose a little bit of physical insight, but it's good because you can find the top quarks. So what happens next? So collider physics is sort of dead, this conventional collider physics, and the question is, what is machine learning going to do next? What is the next field of high energy that it's going to make obsolete? And so far, most of the machine learning applications in physics are highly numerical. This is true in collider physics. It's also true in astronomy and other applications where you have some data, which is, in collider physics we have a lot of events, but it could be other kinds of data. It's highly numerical. And most of the applications have been here. On the other hand, if you look at most of the papers written by this community, for example, they're almost all symbolic. There's a little numerical work sometimes, but almost all of it is sort of manipulating symbolic expressions in some way. And so the question is, can we transition from this numerical approach to the symbolic approach? And my view is that symbolic machine learning methods are really going to be essential for high energy physics. They haven't really done anything yet. But going forward over the next, year, 2 years, 5 years, 10 years, it's really going to be critical to this field in the same way that machine learning has become critical for collider physics. So this talk maybe give you a sense of why I think that's true. So just to give some inspiration, let's sort of say what is state of the art? What is going on in symbolic learning in mathematics and physics at this point? So there was a paper in 2019 by Facebook AI, which they asked the question, can we integrate these differential equations? So here's a differential equation, here's the solution, and what it tried to do is learn the mapping from this type of thing to this type of thing. And it worked pretty successfully for these sort of simple ordinary differential equations. A similar project was done by DeepMind, which is part of Google, and they asked these kind of elementary algebra questions. Can you factorize this polynomial, right? And the answer is x times x plus 7. And so the idea is, you input these and you learn how to do this factorization. Okay, so this doesn't seem so bad. If this is state of the art, if this is what, DeepMind and Facebook AI are doing, we should be able to do similar things like this and make sure that these methods work before we actually move on to problems of actual interest. I mean, nobody cares about doing these things, they're trivial, but the fact that this is an interesting application of machine learning suggests that there should be interesting applications of machine learning in our context too. So the question I'd like to do, in sort of thinking at the big picture, is suppose we have some Feinman diagram. This is a simple 2-loop one, but we could have 3 or 4 loops. Can we use machine learning to just spit out the answer? Right? Can it do the integral? And I don't mean just doing the integral, like plugging it in and doing the integration. I mean in some way doing it in a machine learning way where it sort of guesses the answer. And I'll explain how this works going forward. So is this crazy? I don't think so. We already can automate essentially the computation of 1-loop amplitudes. This is sort of a solved problem. 2 loops, 3 loops. It's conceivable that that there exists a computer program that you give it a Feinman diagram and it spits out the answer. Would this completely revolutionize physics? I don't think so. I mean, I think even if we had the analytic form of every Feinman diagram, we'd still have a lot of work to do. We would still have to study these things and figure out what it means, and it wouldn't really change the world, but it would be helpful. So I think if we had such a thing, such an oracle that given a Feinman diagram would spit out an answer, it would sort of be like having a calculator where you don't have to spend your time doing arithmetic anymore, multiplying numbers or taking square roots. It does it for you, or Mathematica, these kind of tools. So I can envision such a tool existing, and not in the asymptotic future, but in the on the 10-year time scale, something like this existing. And I'd like to sort of work towards it. So what's a simple what's a baby step we can take, baby step of order kind of solving these kind of things. So one thing that comes up a lot is that you have two expressions for an integral and you'd like to know if they're the same. And it's not always so easy to determine whether amplitudes are equivalent. So just an example from my own work is so I had a paper last year where we computed the Compton scattering total cross-section in next leading order. This was with my student Jai Wan and with Roman Lee, which surprisingly hadn't been done. I don't know why, but it wasn't entirely trivial. But basically, as you know, you compute, so you write down diagrams, you reduce them to some sort of iterated integrals. You can often do the integrals. And then you're left with these expressions, which it can be a little nasty. They can have these, the alphabet isn't always the simplest possible alphabet. And then after some work, which actually takes a lot more time because there isn't automated tools for doing this, you simplify it to something that's relatively clean. So I'm interested in focusing, what I'm going to talk about today is the simplification step where you take some complicated expression of polylogarithms and try to write it in a relatively simpler form. So why is simplification important? You can say, well, if I just want to numerically evaluate this, I can do that. I don't need to simplify it. But of course, a lot of physics is about simplification. You don't understand something unless you have it in its simplest form where you understand what's going on. Singularities that are apparent here would cancel. I mean, I think, so this is again philosophy, but in a sense, all of science is simplification. We want to understand complicated phenomena in terms that we can understand. So this is an example of the kinds of things I think machine learning is actually going to be good at, and this is a well-defined problem. So how do we do it? So how do we simplify these polylogarithmic expressions? Well, for logarithms, it's easy. You just use this one identity, the product rule. For dilogarithms, well, there's rules like the inversion rule and the reflection rule and the duplication rule. There's this 5-term identity that was mentioned earlier. This 5-term identity, nobody would actually use it. It's much easier to use the symbol. We've already heard a little bit about the symbol this morning, so I don't need to introduce it. I'll talk about how to use the symbol in the context of machine learning going on. There's identities you can look up for trilogs and Li4 and so on. Let me just make a simple statement. Suppose we have some polylogarithmic expression. Here's some function with Li3s in it. What is the simplest possible form of this expression by some metric? A related question is, does it simplify to 0? It's not obvious, but this expression actually simplifies to 0. And if it does simplify to 0, how do you get there? What polylog identities do you apply to simplify it to 0? So for example, you can find the identities that simplify the leading transcendentality part to 0, and knowing the identities allow you to also figure out the subleading transcendentality part. So that allows you to focus on the leading part, which is a little simpler. So I'm going to talk about two approaches to the simplification problem. One is using reinforcement learning, which I'll discuss, but it's basically like using reinforcement learning, well, I'll talk about it in a second, where you try to put these moves together to simplify a polylog to something simpler. And another method is the transformer network, which is really revolutionizing machine learning, and I'll talk about that too. So let me start with reinforcement learning. What is this? Reinforcement learning, you should think of like AlphaZero or AlphaGo, these programs that solve chess or solve Go. They solve games. This is really the killer app of reinforcement learning. So the idea is you have some set of moves that you can do. So this is a very good mapping to our simplification of polylogarithms. So for example, for dialogues, we have the move reflection, which is like pushing up on your controller, or inversion, which is x goes to 1 over x, or duplication, which actually makes it turns one polylog into two. And reinforcement learning says, okay, I'm going to figure out what order to do these different moves in. And so you have an action, and you have an environment, and you have different internal representations of this information. And it's called reinforcement learning because the idea is you know when you win, which is, for example, if this polylog expression simplifies to 0. And if it's simplified to 0, then you go back and you figure out what the moves you did to get there, and you reinforce the ones that helped. And if it didn't get to 0, you go the opposite way and you reinforce them as negative. So then each time you play, you're more likely to do the better moves based on the current state, which in this case would be the polylogarithmic expression. So here, to map reinforcement learning to this problem, you have a reward function. This is the analog of taking the king in chess. It's when the game is over. And here it's just basically, well, if you reduce the number of polylogs in the expression is our reward function. And this is not the way the machine understands how to evaluate the score like in a chessboard, the machine would take a picture of the chessboard and have its internal way to figure out how good the position is. But the thing you actually tell it is just how to win the game and what the moves are. So it's the same thing here. We're telling it this, and it learns how to look at an expression like this and figure out which moves it should do given that expression. So the way we actually do this is we generate training examples by starting with 0 and then scrambling them by applying identities. So we write 0 as just this, this minus itself, and then we take one of these and scramble it with a duplication identity and then scramble it with an inversion identity, and you get something which looks a little complicated but actually simplifies to 0. So it's fairly easy to generate this data set, and then we're going to train on it and see if we can figure out which moves to do to go backward. So I'll just kind of summarize the results here, which is that it works pretty well. It doesn't work fantastically, but it works better than you could do by hand maybe, or more efficiently. So we wrote a kind of a simple classical algorithm to try out different moves and sort of explore the search tree of these things. And roughly speaking, so there's different ways to do it. You can kind of pick the best move, or you can kind of explore multiple paths through the space at the same time. And we got around 89% accuracy. And basically what it can do is it can simplify things to 0 better than this classical algorithm. So it can, it works. Okay. So let me go on to the next tool, which is the transformer network, which is actually much, much more powerful. And a lot of the rest of the talk will be about transformer networks and what they're going to do and why I think they're really going to revolutionize science in general. So the transformer networks are based on this idea, this paper from Google Brain in 2017, attention is all you need. This paper, for context, has 50,000 citations. It gets 1,000 a day or something now. It hasn't had much effect on physics so far. Of these 50,000 citations, only 28 of them are in high energy physics. But I believe that's gonna change going forward. So what's the idea here? The idea is that it's an autoregressive language model. So a lot of what's going on in machine learning is trying to read text and understand and how to learn from text. And autoregressive means it looks at what's been said before and tries to predict the next thing. And so an example of this, is the OpenAI GPT-3 algorithm, which is actually public in the sense that you can access the trained network and plug in statements and ask it to predict the next words. So it can do things like translate for a second grader. So here's something, this non-disclosure agreement is entered into between the principal offices of this, receiving that, blah, blah, blah. And then it says translate for second grader. It says, this means that if you tell someone something I told you in private, I can't use it to make you pay me lots of money. Right? It's translating it into something you can understand. And this seems like it would be a useful thing for physics. Some of these talks we've seen, I could use translate for a second grader. We can try that afterwards if you want, if someone can give me the text. But it's a very powerful network. I tried it out on multiple algorithms, so I asked it, what are 5 key points I should know when studying multiple polygon algorithms? It's impressive that it actually knows what a multiple polygon algorithm is. But it says it's a generalization of logarithm. They can be used to express a wide variety of mathematical functions. They can be defined in terms of a power series. They can be evaluated numerically. And they have a wide range of applications in mathematics and physics. So these are all true. They're not particularly deep, but it knows something. I also asked it, can you simplify dial algorithms? And it says there's no general way to simplify dial algorithms. Okay. However, there's some special cases where dial algorithms can be simplified. For example, if the argument of the dial algorithm is 1, then the dial algorithm can be simplified to 0. So try that out. Okay, so it's not perfect, but it's getting there. Okay, so what is a transformer network? So it's an example of a sequence-to-sequence model. So in this case, it's like language is a sequence of words, and you're translating it to a different sequence of words. So it uses these things called attention blocks. And this was the big insight of the transformer network over other sequence-to-sequence models, which is that it can understand the context. So for example, here's a sentence, the animal didn't cross the street because it was too tired, versus the animal didn't cross the street because it was too wide. So here you have to know that it refers to the animal, and here you have to know that it refers to the street, right? And of course, in English, it doesn't matter, it's the same word, it, but if you translate to French, you get a different answer because it has a different gender, street and animal, and so you get the translation wrong. And so what attention is it says it knows how to connect this word to previous words. So these are rather sophisticated networks that keep track not just of they're not just doing a word-to-word translation, but they're translating the whole context, not just of the sentence, but the paragraph, and the whole text that you're interested in. And it keeps a rather sophisticated knowledge of a memory of what's going on. And that's really the way to think about it, is it has a better memory than previous memory mechanisms used in machine learning. Okay, so how can we use transformer networks for this task of simplifying polylogarithms? So what I want to do is just use it as a translation task. So I have some expression, here's a polylog expression, and I want to translate it to its simple form. So I'm going to generate data, but this time I don't have to simplify them to 0. If everything's simplified to 0, the translation task would be trivial. So I have expressions, I start with something that's non-zero, and I scramble it up like before. So here's an example scrambled dialog expression. You see these are rather complicated functions, and this is the simplified form, and I'd like to see if it can translate this into this. And so this already seems, it's not, you know, if I gave you this and asked you to simplify it, it might take you a while. So let's see how it works. So just to contrast this transformer network with the reinforcement learning approach, so for reinforcement learning, we have this 0 was the unique correct answer. And so in a sense, reinforcement learning task was easier because you know when you're done. You know when you take the king in chess, the game is over. Here, you don't know what's the simplest expression, so it just has to, you know, guess an answer, and there's no easy way to check. I mean, you can check afterwards, but the network doesn't always know that it gets the right answer, while the reinforcement learning did. But the other thing the transformer network doesn't give you is it just gives you the translation. It'll just tell you this thing simplifies to that, but it doesn't tell you the sequence of moves that you need to get there. So for example, it wouldn't easily be able to give you the lower transcendentality parts of the expression, although you could often reconstruct it afterwards. The other thing is that there can be many equivalent expressions. So here, these are all equivalent to each other by polylog expressions up to lower transcendentality, lower weight functions. These four are all the same. This is not the same. So you kind of want to make sure that if it spits out this one, it could equally well have spit out any of these, and you're not going to say it's wrong when you evaluate it. But that's sort of a technical part. So let me just summarize the results of this. So it works, and in fact, it predicts the right simplified answer 91% of the time. Here we're using scrambles, nine scrambles, and so on. So that was one approach, and so there's a related approach. I mentioned I was going to talk about symbols. So you'll say, well, we know how to simplify polylogs. Why do we bother with these identities? Nobody would actually use a polylog identity. You just compute the symbol and manipulate it. So let's do that. There was some introduction to symbols, so I'm going to skip this part. But the basic point we need is that symbols allow the simplification of polylogs to be reduced to essentially the simplification of logs. So you get this product rule that you can use, which is the essential. Here's the form of it, that lets you simplify dialogs or weight n polylogs in the same way you simplify logarithms. So the idea here is we start with some expression, we compute the symbol, we simplify the symbol, which is actually rather simple to do, and then the real challenge, you don't get it for free, is to integrate the symbol. And this is not an easy task. In general, given a symbol, there's some mappings between functions and symbols. You can go this way, but it's hard to go this way. So what we're going to try to do is use the transformer network, given a symbol, to give the integrated form. For example, here's a symbol, and here's the integrated polylog expression. So we're going to try to learn this mapping. Here's a bunch of examples. Okay, and again, just summarizing the results, we find that actually it works better than the other approach of simplifying the polylogs, and actually we're able to work, you know, we tried up to weight 4, there's no reason to stop other than computing power, but we find, so for example, we get 80% of the time we can simplify a weight 4 polylogarithm expression that has up to 21 terms. And again, it scales very well, and if you train the network longer and you put in higher weight polylogarithms, I think it would go and simplify even more complicated expressions. So this, for me, is an impressive result. It wasn't a very complicated network, and it actually does something that's a non-trivial task that solves a problem that I'm interested in, that I've encountered in my own research. So this was an early test of transformer networks and symbolic regression in machine learning, and it actually already works very well. So an example of a use case of this is, so you do some amplitude, you get some integral in terms of boundary of polylogs, you can write it in terms of polylogs, you calculate the symbol, and then you say, how do I integrate this? And you use the transformer network, and so basically this is the simplified form of that. Okay, but I want to move on, and I want to kind of talk for the last couple of minutes, which I guess I have 3 minutes, to tell you why I said that this is going to revolutionize high energy physics. You may not be impressed with the application I have so far, but I want to talk about the kind of future of machine learning. So there's this program called DALL-E where you can tell it a sentence and it generates an image. So I plugged in Richard Feinman doing a jig in Prague and it generated this picture, which, I don't know, and robots taking over the Charles Bridge gave me this one. It's kind of fun. If you're bored, you can load up DALL-E and start playing with it. So what I want to talk about is why am I so sure that symbolic machine learning is going to revolutionize physics? And the main thing is, what I told you was state of the art when I started this project, but what's state of the art today is this program Minerva, which just came out a couple of weeks ago, actually. So Minerva is based on Palm. So I mentioned GPT-3, which is the OpenAI network, with around 100 billion parameters. This is a 540 billion parameters. Just for reference, the human brain is 80 billion neurons. This pathway model, this is the language model, it was trained for 2 months on 6,000 of these tensor processing units, which is the newer version of a GPU. It took about $23 million to train. So this is really state-of-the-art, Google doing what they can with their biggest network and their most powerful training. And then there was this, so Palm is a general purpose language model. And then there's this program Minerva, which came out recently. So this was June 2022, by a spin-off from Google Research, which involves Google and other people. And in fact, just to be open, this is my former student Anders was one of the authors on this. So it takes on Palm and then retrains it on math stuff. So it tries to learn LaTeX, and instead of just learning text and learning English and other languages, it learns LaTeX, and it learns this from archive papers, and it learns it from various websites that have computations of various things using MathJax or other things. And so it takes this pre-trained network and then does an additional month of training on 1,000 TPU chips. So this isn't something you can do at home, but the question is, what is it good for? So here's an example of what Minerva can do. You give it a question, 4 politicians and 3 lawyers attend a party, each politician shakes hands exactly once with everyone, and each lawyer shakes hands exactly once with each politician. How many handshakes take place? This is not an easy question. You have to think, I mean, you could do it. It's you know, but I don't know. I mean, I can do this. Maybe if I asked my kid, she wouldn't be able to do it. It's not an easy problem. The output of Minerva is this. Let P be the set of politicians and L be the set of lawyers. There are 4 times 3 is 12 handshakes between politicians and lawyers. There are also 4 choose 2 equals 6 handshakes among the politicians. Therefore, the total number of handshakes is 18. Final answer is 18. This is the right answer, but not only did it give you the right answer, it explains how it got it and did this output in LaTeX. To me, this is extremely impressive. There's a whole bunch of other examples. Here's one about a liquid flow. I think it's a multiple choice question. I understand, just another minute or two. And again, it's outputting this in LaTeX. It gives a full explanation of this. These are, high school, early college level physics problems. And it's getting them right with explanation. So even if, maybe it got a number wrong, and sometimes it screws up the arithmetic, it'll explain how to do the problem in a useful way. Another example here is one with a matrix. So let D be a matrix representing a dilation with a scale factor and a rotation, and it wants to decompose this and figure out what it is, and here it gets the answer 5 square root of 2 correct. It's hard for me to overstate how impressive this is to someone who's worked on machine learning for a while. It's solving real-world physics problems and explaining the answer in LaTeX in a way that you can understand it. So what I showed you before, the state of the art was factorizing, x squared minus 7x. And now it's solving college level physics problems. And this was development over like 2 years. That's what's changed. So this field is growing extremely fast. So what's next? Well, so this was, I mentioned first this GPT-3 model, which translated for a 2nd grader. Now I talked about this Palm Minerva model, which has 540 billion parameters, right? And again, comparing, so the human brain is 80 billion neurons and around 150 trillion synapses, which is maybe the better thing to compare to the number of parameters, compared to, say, a cat brain, which has 10 trillion synapses. There's this open GPT-4, which is supposed to come out any day now, which is supposed to have 100 trillion parameters. So the difference between this and this is the difference between, something below a cat and something of order of a human brain. Right? And these are, year scale developments where we're going by, 3 orders of magnitude in computing power. So you can ask, well, what's going to happen next year? And what's going to happen in 2040 or 2100? Right? It's hard to imagine that these networks won't quickly be much better than the human brain. Right? Right now, they're solving problems that, college students might struggle with. right? So what are they going to be doing next year? They're going to be solving problems that graduate students are struggling with, and 2 years after that, you know, the smartest people in the world will not be able to compete with these machines. So not only is the future approaching rapidly, it's already here and quickly going to run us all over unless we're careful. So that's the sort of apocalyptic prophesying that I was worrying about. But the future is here. This to me is really this phase transition that we've been waiting for. And this Minerva project really convinced me that the time is here for machines to really participate in active, useful physics research. So let me just summarize, going back to my boring example compared to what Minerva is doing. You know, well, I just tried to find a simple problem where machines can help with symbolic manipulation, and I found that actually it works. Just, you know, using code, there was some fiddling to do, but it wasn't using 100 trillion parameters, right? We're just using a laptop here and training for a day, and already it can solve a non-trivial problem that's relevant to research. I talked about reinforcement learning and transformer networks, and got something that was 90% accurate. It's also scalable, so if you really had a hard problem that you needed machines to do, you could probably convince someone at Google to do it, and I believe that these methods will be very useful. So again, just taking a step back at the outlook, as I started at the beginning, you know, most of machine learning in high energy has been focused mostly on HEP-PH and mostly numerical, but I really think the future is going towards the symbolic problems, and I really think that the like questions we're asking here, which you say, well, how can machine learning possibly help? If you take a step back and try to think about it, I mean, the main thing you need is some data to train on, and if you can figure out some element of a problem you're interested in, where there's some class of related problems that you can train a network, you'd be impressed with how well it can learn and help solve the problem. So let me stop there and hopefully give you some things to think about. Thanks. Sorry.
All right, we're running a little over time, but I think let's take at least a few questions. Let's see. There's one over there with Lance. Yep.
Thanks a lot for telling us what happens when the S matrix hits the matrix. No, I just wanted to defend GPT-3 slightly by pointing out that in Maple, there's a function called dilog of x, which is polylog 2 of 1 minus x. And so dilog of 1 is 0. So I'm guessing that GPT-3 scraped some Maple expression off the internet to come to this conclusion, and it's only Mathematica users who are confused.
Thanks
anyway,
for that.
Nothing substantive to add.
Thanks for the nice talk. Okay, even though Lance now cleared up this one thing with the dialogue, it still seems like sometimes the networks just get things wrong. Sometimes easy things, sometimes subtle things. So I'm wondering, is there some way of assigning some measure of certainty to the answers? So can you do some heat map of which parts of the answer are very certain or not?
Yes, absolutely. That's a very standard thing to do in machine learning, because you have a loss that you evaluate, and usually, you know, if you're picking the best answer, like for this simplification, you have some probability that this is the right move. Like in chess, you say, well, I think I should move my pawn there, but I'm not that certain. Or you might say, I'm absolutely certain. And you can just tabulate that, and you can put the output with the probability that you think that the confidence you have in this. So yes, uncertainties are a very natural thing to come out of neural networks.
Okay, cool.
So you showed that you train it to know what is a good decision to make in each state. But how, when it's faced with a new state, does it determine, is that state, which data to use? Like, is that state similar to previous states? How does it determine how similar it is to different states? Maybe there's something I don't understand.
You're asking, what does the network know? How does it think about it? And what is the latent representation of the state space?
Like, how does it, if it's trained on some previous states, and it's faced with a new state, how does it just know, how does it determine which previous states lessons to apply and how?
That's a very complicated question, and these networks are very sophisticated, and they use, you know, it's all internal to the network. It's very hard to translate that. If you find a way to probe it, you can ask, you know, what did you use to determine it, right? And maybe you can get an answer out of that, but generically, it's internal to the network, and you just get the output. And this is a drawback of transformer networks, where you don't know how it's doing the translation. But in the same way, if I ask you to translate something to French, And I asked you, how did you know that was the right translation? He was like, I don't know, how did I know? You know, it's not always so easy. And partly it's the way the computation is done internally that makes it powerful. It's also what makes it hard to explain. But it's part of a broader question of interpretability, which is a big deal in machine learning, and there aren't any easy answers.
Okay, thanks.
So in view of time, I think we should thank Matt again. And as our final talk of the day, Kongkao Wen will be telling us about some exact results of n = 4 super Yang mills and S duality. So go ahead.
Thank you. Let me begin by thanking the organizers for inviting me and have the opportunity to speak. I really wish I could attend the conference in person. Anyway, so I will talk about exact results, some exact results in n = 4 super Yang mills and their applications to S duality. So this is based on some theories paper I wrote with Daniel Dolegoni, Michael Green, also a master student, Haijing Xie, and also a PhD student, Songqian Zhang. I think he's supposed to be in the audience. Yeah, you have heard a lot of, say, remarkable progress in understanding n = 4 super Yang mills in various directions. So I will actually discuss a much older story of n = 4 super Yang mills, namely the S duality. So just to be very concrete, so we like to understand how the correlation function behave under the modular transformation. Because the duality relates strong and weak coupling, and also involve non-perturbative effects. So it will require us to, say, compute the correlator at the finite Yang mills coupling. Finite, I mean, including the, say, theta angle, namely for the instanton effects. I think in some slides, I will call this tau as tau 1 plus I tau 2. Good. So just remind you, sorry. So let me just remind you what is S duality. So if you begin with, say, n = 4 super Yang mills with the gauge group Gn, and the transformation, there's two kind of transformation. One called translation. So and the gauge group is unchanged, whereas under the other transformation I call the S hat here. The gauge group in principle changes. It depends on what the gauge group you start with. So that, well, in the case I will consider just the classical gauge group. So you have in the case of the simple laced groups SUN and SO2N, the theory is self-dual, whereas for non-simple laced group SO2N plus 1 and the USP2N, the gauge group actually exchanges under the S hat. So all those properties should reflect in the physical observables, in particular the correlation function, which I will consider. Okay. So the correlation function I will study is a very standard one which has been studied for decades. So I will consider, well, basically the simplest operator. I call O2 here since it's dimensional 2. It's, well, build out the two scalars in and, well, because SO6 symmetry, it has index run from 1 to 6, so it's very convenient to contract the index out by introducing this now vector. The reason it's now because I want to get rid of the Kunichi operator. So this is known that the 2 and the 3 point function of this operator are protected. The first non-trivial case is 4 point. It's convenient to separate out a free part, which means that this part you can compute just by weak conjunction. And we will really just focus on the remaining part. And the remaining part can be further decomposed into two pieces. It's sometimes called the partial non-renormalization theorem, where there's a prefactor I called I4 here are completely fixed by symmetry. And this I4 contains all the information about the R symmetry since it's a functional yi. So this one, for amplitude, you can think of it as a delta Q. So delta Q tells you like which helicity you are looking for. And this plays the same role here. So eventually I will really just focus on this single function. It's a function of the cross ratio, of course, and functional coupling, and also depend on the gauge group. Very good. So as I emphasized, to study the modular property, I really want to compute the correlate at the finite coupling. I guess it's pretty obvious that it's very difficult. Well, I would say it's impossible. So rather, we will consider a much simpler, yet highly non-trivial object, at least for my purpose. And this is something we call the integrated correlator. Definition is very simple. So you take the correlator, namely the non-trivial part, and you integrate out the space-time now or cross ratio with a certain choice of measure. And the statement is that when you choose the measure properly, this object, namely the integrated correlator, maybe can be computed exactly. I won't discuss this in detail, but if you insist, you really want the space-time dependence, turns out at least for the first few orders in the Lagrange expansion, once you have integrated correlator, you can actually reconstruct the space-time dependence. So there are two integrated correlators have been studied in the literature. So the measure is given by here. Probably at this point, it's not so important what is the precise measure, but anyway, there are two of them. The first one given by here, the measure I highlight here, and the second one is basically the same, but you insert yet another box integral. For some reason, it was called D111 because it's related to the Witten diagram. Anyway, just one loop box in 4 dimensions. Oh, good. So, but before I jump into, say, non-perturbative effects, since this is the amplitude, so it will be shame if I do not talk about the any loop integrals. So let me begin with a perturbation and talk about the loops. As I mentioned, this correlator was studied for decades. A particular aspect that relevant for this part of the discussion was this papers. I should also mention, I think Shungqing gave a gong show and the poster on this piece of work. Anyway, so they realized the integrand for this correlator has this kind of enhanced permutation symmetry. So say if you're interested in L loop, it turns out instead of say SL4, so SL times S4, there's a full permutation symmetry with L plus 4. And so what you do is that you just draw those kind of permutation invariant graph with this number of vertex. And basically, because of conformal symmetry, you want each vertex that has weight 4, namely there are 4 propagator connect to each vertex. And at one loop, this is basically the only thing you can draw. So as I said, 4 of them are external points, but 1 of them is internal, but they are on equal footing. And this is a 2 loop, and this is a 3 loop. In 3 loop, it turns out that you need some vertex which has 5 propagators. Then you join it with a numerator such that each vertex is still with 4. Okay, very good. And the story about the integrated correlator is that they are just the so-called periods of those F graphs. And in practice, what you do, so instead of you integrate out, say at one loop case, instead of you integrate out X5, you integrate out all the points. And of course, if you do that, it's divergent because the integral is conformal invariant, so you remove the conformal symmetry. And this such object was studied by many people. In particular, it appears in the study of say vacuum diagram of 5-4 theory. But of course, we have more than 5-4 because in certain cases we will need numerators. anyway, this was well studied, and there's a program to compute all those periods, and so we use those programs to do it. And for the second integrated correlator, as I mentioned, the story is very much the same, but now you insert the box, but still it's periods, and you can compute it. Very good. So let me come back to my original motivation. So we want to compute this at the finite couple. This was achieved by understanding that how those integrated correlators are related to the partition function of N2 star super Yang-Mills. So N2 star super Yang-Mills, you can think of that N4 super Yang-Mills deformed by some mass term. And when you set the mass to 0, you go back to N4 super Yang-Mills. So that's why I said, in all those formulas, I set the mass to 0 at the end. So there's such relation. I won't really explain, but I will make a comment. The whole point of relating, say, the integrated correlator to the partition function of N2 star super Yang-Mills is because the partition function of this theory was famously known, can be computed from supersymmetrical localization. So I won't really go into any detail about the localization computation, but let me make a few comments. The first thing I already mentioned, it is not surprising that when you take a four derivative on the partition function, you will find the integrate 4-point function, because taking four derivative, roughly speaking, you bring down 4 integrate operators. What is non-trivial is that when you do that, if you do it, if you look at into detail, you realize you bring down a bunch of kind of different operators instead of just O2. So what you need to do is to using super conformal transformation to bring all those operators into O2. So that generates a lot of, say, factors, and those factors combined together gives precisely all those, say, measure I mentioned earlier. Okay, so, and as I already emphasized, it's great that the localization reduce partial integral to n-dimensional integral, but nevertheless, it's not easy integral. In particular, say I want to compute it for arbitrary n, and furthermore, for my purpose, the many properties, especially the SL to Z property, are not manifest. I promise that I don't want to discuss any localization computation, but if you are familiar, this the instanton contribution, sometimes called the Nixon partition function, is quite a complicated object. In particular, say if you want to compute say arbitrary number of instantons, this will be k-dimensional counter integral, and you have to do the residues on this Yang tableau and so on and so forth. So all my comments try to say that localization is great, at least for this particular case. We hope we can do better. So after analyzing the localization formula, basically did a lot of examples, and we found that this, at least for the first integrated correlator, can be written in this extremely compact form instead of n-dimensional integral with a k-dimensional counter integral. So it can be written in this extremely compact form. In particular, the coupling dependence only appear in this particular combination. So PQ are integer, you sum over. And it's easy to check. So when your coupling appear in this particular combination, it is SL to Z invariant. So SL to Z is manifest. And then really all the non-trivial information is contained in this rational function. I call it BSUNT. Really all the non-trivial information is in the numerator of this rational function. And this numerator is some polynomial, which we know exactly what it is. So here I just give you a couple examples for SU2 and SU3. So let me just emphasize one more time. So say just for SU2, we claim that any number of instanton contributions for this integrated correlator just contained in this rather simple polynomial. Good. You can say manipulate a little bit of the formula and find that you can re-express the expression in terms of as some formal infinity sum of non-holomorphic Einstein series. Here I gave you the definition of non-holomorphic Einstein series in the Schwinger parameterization form. Once you write in this form, it's obvious to see why this is possible, because what you do is you just expand this rational function in power of t, right? So each power ts just becomes a non-holomorphic Einstein series. And the non-holomorphic Einstein series contains perturbative terms and instanton terms. So therefore, this expression contains all the perturbative terms as well as instanton contributions. So this sum, you can, well, it's not surprising. You can just rewrite that as an integral along the imaginary line, and that leads to so-called SL2 spectrum representation for this integrated correlator. So let me maybe remind you, this is a well-known story in mathematics. So any SL2 invariant object can be, say, decomposed into continuous spectrum, namely non-holomorphic Einstein series, as well as discrete spectrum called the Cusp forms. So for some reason, which a priori not clear why, for this integrated correlator, Cusp form do not appear. But this is only clear when you have this formula. So before, with the formula, I wouldn't be able to guess why there's no Cusp form. One can prove the formula we proposed, at least in a, say, maybe not the direct way, but indirect way. So first of all, for SU2 case, one can actually do the localization computation explicitly and check that the formula is correct. And then we can prove some kind of so-called Laplace difference equation, which takes this form, but the only point is that it's a recursive relation, namely it relates the integrated correlator with different rank of gauge group. Therefore, with this equation and proper boundary condition from perturbation, you can determine, say, the integrated correlator for any gauge group in terms of SO2, which we checked explicitly. And so, in fact, one can even do better. We recently found one can even find the generating function for this integrated correlator by resumming all the n. So the point that you just take the the integrated correlator, then you resum n. In our expression, what it really means is just to find the generating function for this rational function I only gave you for SU2 and the SU3 case. And if you do that, amazingly, that's the expression you would find. So we claim that for this integrated correlator in the SU theory for arbitrary n, it's all contained in this simple expression. And we actually derive this formula by understanding how this integrated correlator is related to something called Harari-Zagier formula in the, it's a very well-known formula in the matrix model literature. Good. So now we have this exact expression in the remaining, I don't know how many minutes. I will study this object in various region. For instance, the standard small G-Amuse expansion or large N expansion, and etc. Okay, let me begin with the standard loop expansion. If you take that object and you expand it in G-Amuse or lambda, that's what you would find. I guess expression is not so important, but let me make a few comments. So one is that the non-planar contribution only starts as, well, it's evident here, only starts at the for loops. So this actually was known in the literature that this correlator, for some reason, the non-planar contribution and late. And well, here is a confirmation as well. And well, of course, we can give all loop prediction for what it is. As I mentioned earlier, that for the perturbative part, there's a very interesting connection between this integral correlator and the periods of this conformal Feinman integral. So using those wonderful machinery and package, we were able to do those integral explicitly, say up to 4 loops, and indeed we found a precise match with those numbers given from localization. For higher loop, in particular, say 5 loop, there was one integral we were not able to do. On the other hand, since we know the result from localization, so in some sense, that gives a prediction for that particular integral. And well, we were not able to check it. Then there's a standard, say, larger n expansion. So you can expand the, say, small lambda or large lambda. So let me begin with small lambda expansion. Well, once again, I guess the expression is not so important. So let me just make some comments. It turns out, as probably already known by studying other physical observables in enforceable Amuse, that the large and small lambda expansion is always convergent and with a finite convergent radius. Then similarly, you can do large lambda expansion. And so evidently now the expansion is in terms of half integer power of lambda. And once again, for the Cusp, people already notice that the large lambda expansion is asymptotic, not Boole-Sangable. So therefore, it requires, say, some non-perturbative completion. In particular, you need say exponential decatur goes like e minus square root of lambda. Okay. Well, it turns out there are actually another type of exponential decatur, which may be not so familiar. It goes like exponential n. So we do large lambda, sorry, large n first, then large lambda. So it's say exponential decay in m. This was also found very recently in this paper. So in the next slide, I will claim that these two should appear together due to SL2Z. So to study SL2Z at the large m, so what you would do, well, as I already emphasized, to study SL2Z or modular property, you really should consider finite coupling, finite tau. So we will do large n expansion, but keep the Yamuse coupling finite, not using lambda. So in the literature, this is probably called a very strong coupling limit. And well, you just do it and you find there's expansions and the coefficient of those polynomial terms is given once again by non-holomorphic Einstein series, which appeared before. So if you're familiar with the story, because this is due to the string amplitudes in ADS5 cross F5. So the first term basically is the supergravity term. This is the R to the 4 term, and this is the D4 R to the 4. And indeed, at R to the 4, that coefficient E3 half, and the D4 R to the 4 was famously known, that coefficient E5 half. So besides all those, say, Laurent-Taylor term, there's an exponential decay term, which goes like a square root of n. As I claimed, so well, so this writes as a say virtual PQ string instanton. So to compare the previous slide, which is a 0 instanton, so I need to take a so the instant number is p times q. So I need to either take a p equal to 0 or q equal to 0. If you do that, then you precisely reproduce the exponential decay term I mentioned in the previous slide. So let me finally go to say the integral correlator with a general classical gauge group. So I have spent a lot of time on SUN. Let's look at the general classical gauge group. So first, let me begin with the simple list groups, which are SUN and SO2n. In this case, well, the theory is SO2Z invariant. Therefore, the correlator is SO2Z invariant, as I already discussed in length for SUN. So SO2n basically takes the same form, except that this rational function will be different. Maybe a slightly more interesting case is the non-simple list group, which is a USP2n and SO2n. The theory is not invariant from the table I show you. It's only invariant under so-called congress subgroup gamma 02. Okay, sorry. Gamma 02. And GNO duality implies the theory should exchange under this S hat action. So, to realize this, we made the ansatz, and the ansatz is the following. So you'll probably remember the first term, and we claim you actually need a second term, which is very much the same as the first one, except that you take tau, go to 2 tau. For this to happen, you require this two rational function to exchange for these two different gauge groups. So if you trust me that once you have these properties and under S hat, indeed, this will happen, namely GNO duality. Of course, this is just ansatz, and to realize the GNO duality, we have to check, indeed, this gives the right answer. We checked a lot of examples, indeed, that's the correct answer. So let me actually stop here. So since I go slightly over time, I will just leave this slide for you to read. Thank you very much.
All right. Do we have any questions for Conka? We have one up in the back.
So you commented on that the 1 over lambda expansion is asymptotic, not Borel-summable. What about 1 over n expansion of fixed lambda? Was that also not Borel-summable?
Yeah. Right. So 1 over n fixed tau. You fixed tau?
No, not fixed tau, fixed lambda.
Fixed lambda.
Yeah. So I'm talking about like the string coupling expansion, the fixed background, the holographic dual.
Yes.
So for that, the 1 over n expansion in this observable, is that also asymptotic and not Borel-summable?
Yes, I think so. So there's exponentially like minus n term.
No, but that's logically separate from the Borel-summability of the perturbative series, right? So you can have the perturbative series that's Borel-summable, and then you have these e to the minus n corrections on top of that. So what I'm wondering is whether the perturbative series in 1 over n is Borel-summable or not.
1 over n for fixed lambda.
Yes.
Yeah, I didn't look into that. Yeah, that's a good question. No, I didn't look into that.
Okay. And I guess I'm also wondering whether there are e to the minus n square effects in these observables.
No, we didn't see that. So this is one, as I mentioned, and the other one is a fixed tau. That's the behavior we found.
So I guess you would say that this, if you organize this into, you can organize this into terms of sort of e to the minus n, and for each, these are like the instanton effects, and they give you everything. You don't have gravitational instanton effects on top of that.
Yeah.
Okay. Thank you.
All right. Are there any additional questions? Okay, then let's thank Kong Kao again.